Immediate headline deconstruction. The universe may be a simulation, and physicists just slipped up. This headline employs a classic clickbait structure. The first clause posits a mind-bending, sci-fi friendly hypothesis. The second clause creates intrigue and a sense of urgency. It suggests that authoritative figures, physicists, have inadvertently revealed a truth they typically keep guarded. Slipped up implies a mistake, a breach of professional decorum, or an unintentional admission that lends credence to the extraordinary claim. It frames a philosophical and speculative idea as a breaking news story with insider revelations. What constitutes a slip-up in physics? In the rigorous world of theoretical physics, a slip-up is rarely a clerical error. Here, it refers to a consequential, unintentional revelation or concession. This could be a respected physicist in an unguarded interview, admitting the hypothesis is more plausible than they publicly state. A peer-reviewed paper that inadvertently provides a framework testable for simulation theory, or a lecture where a scientist acknowledges that certain quantum or cosmological anomalies are compatible with a computational model of reality. The slip is treating a fringe idea with mainstream scientific seriousness. The incident, analysis of a recent paper, lecture, or interview. While such headlines often refer to past events, e.g., Neil deGrasse Tyson or the late Stephen Hawking discussing its probability, a recent incident might be a between 2022 interview or panel discussion, where a physicist like Kawase Sabutake, David Deutsch, Gary Sasaki, quantum computation pioneer, or Dirapi, James Gates, a Sabaki, who found error-correcting codes in supersymmetry equations, discuss the informational nature of reality. Another candidate is the ongoing work in quantum gravity and holography, where papers on the holographic principle, the idea our 3D universe is a projection from a 2D surface, are sometimes interpreted as lending indirect support to a simulated information-based reality. Who are the physicists? Key figures. The headline generalizes, but specific figures give it weight. Nobel laureates. Frank Wilczek, Nobel 2004, has written on the physics of information. Kip Thorne, Nobel 2017, explores the nature of reality through relativity. Quantum theorists. David Deutsch, father of quantum computing, argues the universe is computational. John Archibald Wheeler, famously coined it from bit, suggesting physics arises from information. Cosmologists. Martin Rees, UK Astronomer Royal, has stated simulation is a legitimate philosophical possibility. Lisa Randall and Adiabai Brian Greene have engaged publicly with the idea. Technologists. While not physicists, Elon Musk and Fabrik Ray Kurzweil, they have popularized the argument, often citing these physicists. Distinguishing the scientific hypothesis from pop culture, The Matrix. Pop culture's The Matrix depicts a conscious experience. Brains in vats fed sensory data by malicious AI. The scientific hypothesis is fundamentally different. It proposes that the fundamental substrate of reality itself is computational, operating on discrete mathematical rules at the Planck scale, the smallest possible scale. There is no real world outside to jack back into. The code is reality. The simulators are not necessarily antagonists, but could be post-human scientists running cosmological models. The core claim: finite discoverable rules, like a computational system. The core claim is that the universe behaves as if it runs on a soireitai, finite, albeit vast, set of rules, physical laws, processable by a system with finite resources. Evidence cited includes the quantization of everything, energy, space, time. Reality has a pixelated or discrete minimum unit, the speed of light as a cosmic processing speed limit, quantum indeterminacy and wave function collapse as possible artifacts of computational optimization or rendering processes. Defining simulation in this context. Here, simulation is not a fake illusion, but a causal information processing reality. It is a fully physical universe whose operational mechanics are best described as computation. Reality is seen as a giant quantum computer or a cellular automaton, like Conway's Game of Life, where simple local rules generate complex global behavior. The simulation is the process of these rules executing. The philosophical precursor, Nick Bostrom's 2003 paper. The modern argument was formally laid out in Philosopher. Nick Bostrom's seminal 2003 paper, Are You Living in a Computer Simulation? He shifted the question from metaphysics to a probabilistic argument based on future technological capabilities, making it a subject for rational analysis rather than pure speculation. Breaking down Bostrom's trilemma. Bostrom's argument is a logical trilemma. At least one of these three propositions must be highly likely to be true. 1. The extinction hypothesis. Almost all human-level civilizations go extinct before becoming technologically post-human, capable of running realistic ancestor simulations. 2. The non-interest hypothesis. Post-human civilizations have virtually no interest in running a significant number of ancestor simulations. 3. The simulation hypothesis. We are almost certainly living in a computer simulation run by a post-human civilization. The force of the argument is that if you believe 1 and 2 are false, that is, if many civilizations survive, and civil men are interested in running simulations, then 3 must be true. The statistical likelihood argument. This is the crux of the probability argument. If even one post-human civilization runs vast numbers of high-fidelity ancestor simulations of their past, the number of simulated minds would astronomically outnumber the number of original biological minds. If this occurs, a random conscious being like you is statistically far more likely to be one of the simulated ones than one of the original biological ancestors. Therefore, unless you are the first and only civilization, or they all choose not to simulate, it is probabilistically likely we are in a simulation. This is a modern version of the Copenhagen interpretation of probability applied to our own existence. Major critiques of Bostrom's statistical reasoning. Bostrom's trilemma, while logically structured, faces significant critiques. The independence assumption. The statistical argument assumes you are a random sample from the set of all conscious beings. Critics argue our evidence that we are early 21st century humans asking this question is not random. If simulations are typically of specific historical periods, we might be in unique original base reality simply because we are at the dawn of the simulation creating age. This is an Auwitz observation selection effect. Problem. Substrate independence, doubt. The argument assumes consciousness can be uploaded and run on a different substrate, silicon. This is a philosophical assumption, functionalism, not proven by physics or neuroscience. Motivation and resource limits. It assumes post-human civilizations would have near infinite computing power and a compelling reason to run vast numbers of detailed ancestor simulations. Both are debatable. The energy and computational requirements for a universe scale simulation may be implausible, even for an advanced civilization. Infinite regress. If we are in a simulation, are the simulators also in a simulation? This leads to a potentially infinite regress, undermining the statistical weight of the argument. From philosophy to physics, when did the shift happen? The shift from a pure philosophical thought experiment to a topic engaging physicists began in the late 2000s and early 2010s, driven by two parallel developments. One, the rise of digital physics. Pioneered by thinkers like Edward Fredkin and Stephen Wolfram, this view posits the universe is a computational process at its core. This provided a conceptual framework. 2. Convergence from fundamental physics. Discoveries in quantum gravity. Like the holographic principle, quantum information theory, and cosmology. Increasingly described reality in informational terms. When physicists like John Wheeler, it from bit, and Seth Lloyd, the universe is a quantum computer, began using this language, it created a bridge. The hypothesis stopped being, are we in a simulation, and became, if the universe is a computation, what are its observable properties? This reframing made it a speculatively testable scientific idea. The role of quantum mechanics in opening the door. Quantum mechanics is the primary reason physicists take the idea seriously, because it behaves like a computational process. Quantization. Energy, angular momentum, and other properties come in discrete packets. Quanta, analogous to digital bits. Wave function, collapse. The transition from a probabilistic superposition of states to a definite measurement outcome is eerily similar to a lazy rendering process in video games where details are only resolved when observed. Indeterminacy and non-locality. The fundamental randomness, Heisenberg, uncertainty, and entangled connections could be interpreted as fundamental ACI protocols or limits of the underlying computational framework, not bugs. The role of cosmology and fine-tuning cosmology provides another pillar, the F of fine-tuning problem. The fact that dozens of physical constants, like the strength of gravity, are precisely set to allow for stars, planets, and life is one of the greatest mysteries. Two dominant explanations are the multiverse. There are infinite universes with random constants, and we happen to be in a viable one. And design. The simulation hypothesis offers a third. The constants are Tauatisabauchen input parameters set by the programmers. The universe's law-like mathematical order is what you'd expect from a design system. The concept of evidence. What would verifiable scientific clues look like? True evidence wouldn't be a glitch in the matrix deus ex machina. It would be anomalies in high-precision physical data that are best explained as artifacts of a computational model, such as unambiguous signs of a discrete spacetime, pixelation, at a fundamental scale, evidence of an underlying lattice structure to the vacuum of space, conservation laws breaking down in ways suggestive of rounding errors or resource limits, foundational mathematics revealing optimization shortcuts. Category 1. Resolution limits to reality, pixelation. Just as a digital image breaks down into pixels when zoomed in, a simulated reality might have a fundamental resolution. In physics, this is the search for a minimum length and time, below which the concepts of smooth space and time break down. The prime candidate is the Farico-Planck scale. 10 zone, torture 35 meters, it's 10, 43 seconds. If experiments could ever probe this scale and find evidence that spacetime is not smooth but granular or composed of discrete bits, it would be a major point in favor of a computational reality. Category 2: Conservation laws as resource management. In a simulation, conservation laws, like energy and momentum, are excellent programming tools to ensure stability and avoid system crashes. They prevent energy from being created for nothing, which would overwhelm the processor. Furthermore, the cosmic speed limit, c, can be seen as about a processing rate limit. Information cannot be updated across the system faster than this, preventing synchronization errors. The finite speed of light ensures causality is maintained in the simulation's processing queue. Category 3: Mathematical underpinnings and cheats in the code. A simulator might use elegant compressed mathematics to generate complexity, or employ cheats for efficiency. Symmetries and group theory. The deep mathematical symmetries, like SU3 XSU 2XU adv1 for particle physics, governing reality, could be seen as the efficient foundational code. Approximations. Just as video games use simplified physics for distant objects, our universe might have approximations. For example, some interpretations of quantum field theory's renormalization, a mathematical trick to remove infinities, have been humorously called the universe's way of hiding its programming shortcuts. Category 4: Anomalies and glitches. While sensationalized, the idea is to look for statistically significant violations of established laws that have no other good explanation. Examples physicists have, very speculatively, discussed include the axis of evil, an unexpected large-scale alignment in the cosmic microwave background radiation, which some have jokingly called a signature of the programmer. Mainstream cosmology largely attributes it to statistical flukes or systematic errors. Violation of Lorentz invariance, finding that the laws of physics change slightly depending on direction or velocity, which could indicate an underlying computational grid. Discrete energy levels in empty space, finding that even a perfect vacuum has energy that can only take on specific discrete values. Introducing the Planck scale, the universe's potential pixel size. The all-Planck scale is the regime where quantum gravity effects dominate. It is derived from fundamental constants, gravity, light speed, quantum action, and represents the scale at which our current theories of space and time predict their own breakdown. The values are unimaginably small. Planck length, weight 1.6, x 10 power 35 meters. Planck time, 5.4 picaba x 10 power 44 seconds. If spacetime is pixelated, these are the leading candidates for the pixel size. We are currently about 16 orders of magnitude away from being able to probe the Planck length directly. However, some quantum gravity theories, like loop quantum gravity, predict specific testable effects from this discreteness at slightly larger scales, offering a potential future path to gathering evidence for or against a computational fabric of reality. Planck length, the shortest meaningful distance. The Planck length, 1.6 and 616 x 10 to 35 meters, is not just a very small number. It is a fundamental limit derived from nature's constants. Gravity, g, light speed, Sebauch, and the reduced Planck constant, I. It is the scale at which quantum fluctuations in spacetime itself are believed to become so violent that the very concepts of length and allocation lose meaning. You cannot measure a distance smaller than this because the energy required to probe it would collapse into a microscopic black hole. In the simulation analogy, it represents the ultimate resolution of the display. the smallest possible addressable point in the fabric of space. Planck time, the shortest, meaningful tick of the clock. Similarly, Planck time, 5.391 x 10 of 44 seconds, is the time it takes light to travel one Planck length. It is the condensing smallest possible unit of time. With any physical meaning, processes that occur faster than this cannot be causally connected, as cause and effect break down. In a computational framework, this is the entity's clock cycle of the universe, the discrete tick at which the state of the universe updates. Events happening at a finer granularity are not just unmeasurable, but physically nonsensical. The implication: reality may be discrete, not continuous. The existence of these fundamental minima strongly suggests that at its bedrock, reality is not the smooth, infinitely divisible continuum described by Einstein's general relativity. Instead, it is granular, pixelated, and discrete. This is a direct parallel to digital systems, which operate on discrete bits and clock cycles. The continuous physics we experience, like planetary orbits, would then be an emergent, large-scale approximation of an underlying digital process. Much like a smooth movie, emerges from 24 discrete frames per second. Digital versus analog. The historical debate in physics. Historically, physics has oscillated between analog and digital views. Classical physics, analog, Newtonian mechanics and electromagnetism described a perfectly smooth, continuous, and deterministic reality. Quantum revolution, digital, the discovery that energy, light, and angular momentum come in discrete packets, quanta, force a shift. The universe was revealed to have a graininess at small scales. The modern quest for a theory of everything is, in part, an attempt to resolve the clash between the continuous geometry of general relativity and the discrete quanta of quantum mechanics. The digital physical view posits that discreteness wins at the most fundamental level. The failure of classical physics to explain the discrete nature of quantum phenomena. Classical physics catastrophically failed to explain phenomena like the ultraviolet catastrophe, infinite energy from a hot object, and the discrete spectral lines of atoms. This failure necessitated quantum theory. The core insight was that properties like energy are quantized. They can only take specific jumpy values, like the rungs on a ladder. This inherent discreteness is unnatural for an analog, continuous system, but is the hallmark of a system operating with finite states and rules, a computational system. Wave-particle duality as a potential rendering effect. One of the deepest quantum mysteries is that entities like electrons and photons behave as both spread-out waves and localized particles, depending on how we interrogate them. In the simulation framework, this could be interpreted as a resource optimization technique. The unobserved wave function is not a physical wave, but a probability cloud, a set of instructions for where the particle might be rendered. Only upon measurement, interaction requiring a definite outcome, does the system render the particle at a specific location, collapsing the wave function. It's akin to a video game not calculating the precise physics of every leaf on a distant tree until the player looks at it. The double-slit experiment as a core mystery. The double-slit experiment epitomizes wave-particle duality and the role of observation. Unobserved. A single electron fired at a barrier with two slits produces a Tate interference pattern on the detector screen as if it went through both slits as a wave and interfered with itself. Observed. If you place a detector to see which slit the electron goes through, it behaves like a particle, goes through one slit, and the interference pattern vanishes. This suggests that the act of acquiring which path information changes the behavior of the system. In simulation terms, it's as if the system only calculates the detailed particle-like trajectory when that information is logged by an observer. Otherwise, it uses a more efficient, probabilistic wave algorithm. The observer effect. Does observation force a state to be rendered? The observer effect extends beyond the double slit. In quantum mechanics, a system exists in a superposition of all possible states until it is measured. The measurement collapses the wave function to one outcome. From a computational view, an observation is any interaction that forces a quantum system to correlate with a macroscopic, irreversible record, like a detector click or a conscious brain. This could be seen as the point where a probable unrendered state must be committed to a definite value in the simulation's memory to maintain consistency for all subsequent processes. Quantum entanglement, spooky action, as a result of non-local processing or optimized code. When two particles become entangled, their properties are linked instantaneously across any distance, defying classical locality. Einstein's spooky action at a distance. In standard physics, this is explained by quantum non-locality and the integrity of the wave function. In a simulation framework, two interpretations emerge. Non-local processing. The simulation does not need to send a signal between the particles. Instead, it updates their states globally from a single reference frame, the programmer's frame, respecting the overall rules but not local causality. Optimized code, pre-computation. The particles' correlated outcomes were never independent variables. They could be the result of a single instruction or shared random seed set at their point of creation. Their seeming communication is just the revelation of this predetermined correlated data when read by observers, an efficient way to simulate correlation without real-time communication. Introducing the holographic principle. The holographic principle is one of the most profound concepts in modern theoretical physics that directly feeds into simulation-like ideas. It posits that all the information contained within a volume of space can be encoded on its boundary surface. For example, the 3D world we experience could be a projection from information stored on a 2D surface at the universe's edge, like a cosmic hologram. This drastically reduces the informational requirements to describe reality, which is precisely what an efficient simulation would do: store and process data in a lower dimensional form and project it into the experienced reality. It suggests the universe is fundamentally an informational structure, a karaoke, and our 3D reality is a derivative emergent phenomenon. The information content of a black hole is proportional to its surface area, not volume. This is the revolutionary insight that sparked the holographic principle. Classical intuition suggests that the information describing all matter and energy swallowed by a black hole would be proportional to the of volume inside its event horizon. However, Jacob Bekenstein and Stephen Hawking discovered that a black hole's entropy, which in quantum information theory is directly linked to its information content, is proportional to the surface area of its event horizon, specifically area to 4 in Planck units. This means a black hole, the densest object imaginable, holds a finite amount of information painted on its surface. It suggests that 3D volume is an illusion. The true degrees of freedom live on a 2D boundary. The universe as a 2D information structure projected into 3D. The holographic principle generalizes the black hole finding to the entire cosmos. It proposes that our entire 3D universe, with all its stars, planets, and galaxies, is a projection from information encoded on a distant 2D surface that surrounds us. Like the cosmic horizon, we are the hologram. Our lived experience of three spatial dimensions is a rich, emergent phenomenon generated from interactions of quantum bits, pixels, on this vast lower dimensional screen. This isn't just a metaphor, it's a rigorous framework within string theory and quantum gravity. This directly implies a computational process. The holographic principle's core claim that the universe is fundamentally an informational structure is the strongest bridge yet to computationalism. Information processing requires a processor and rules. The mathematics of holography, like the add-CFT correspondence in string theory, explicitly shows a duality. A key, quantum gravitational theory, in a volume, is perfectly equivalent to a quantum field theory, without gravity, on its boundary. This is a precise mathematical mapping of one set of laws into another, akin to Song's software emulation. The universe's physics could be the result of running the code defined on the boundary. Jacob Bekenstein and Stephen Hawking's work on black hole thermodynamics. In the 1970s, Bekenstein proposed black holes have entropy, a measure of disorder, chalk information, defying classical views that they were featureless. Hawking then showed black holes emit radiation, Hawking radiation, and have a temperature, cementing them as thermodynamic objects. Their combined work established the formula for black hole entropy, S tardeo Ka, for LP2, where A is area, K is Boltzmann's constant, and L_pub is the Planck length. This equation, simple and profound, planted the seed for the informational view of spacetime itself. Gerard 't Hooft and Leonard Suskind's formalization of the holographic principle. In the 1990s, these physicists took the black hole result and dared to apply it universally. Gerard 't and Hooft first proposed that the principle could be a general law of nature to solve the information paradox, suggesting all physical processes within a volume can be described by degrees of freedom on its boundary. Leonard Susskind gave it its name and powerful conceptual framing, vigorously defending it, and later, with Juan Maldacena, providing the first concrete, mathematically rigorous example within string theory, the ADDS CFT correspondence. This turned a provocative conjecture into a cornerstone of modern theoretical physics. Current experimental tests of holography. While a full test is currently beyond our reach, physicists are devising ingenious indirect probes. Cosmic microwave background, CMB. Some models predict specific statistical imprints, non-Gaussianities, in the CMB if the early universe had a holographic phase. Data from telescopes like Planck are scrutinized for such signatures. Gravitational wave detectors, LIGO Virgo. The holographic noise is a hypothesized jitter in spacetime at the Planck scale. Some experiments are attempting to detect this faint noise using interferometers, as it would manifest as a fundamental limit to the precision of measurements. Tabletop quantum systems. The ADD-CFT duality allows physicists to model complex quantum gravitational phenomena, like black holes, using controllable quantum systems, like cold atoms or ion traps. Observations in the lab can test predictions of the holographic description If the universe is a simulation, what is the computer? This is the ultimate hardware question. The computer cannot be a classical silicon-based machine in a room. It would be too slow and require its own universe. The leading speculation is that it is a fundamental physical system operating on the laws of its own base reality. It is the substrate on which our universe's code is executed. Critically, this means the computer is not magical. It obeys the physical and informational constraints of its own reality, which are likely as inscrutable to us as a silicon chip is to a character in The Sims. Speculation on substrate, quantum computer in a higher dimensional universe. The most coherent guess for the substrate is a large-scale quantum computer, or a network of them in a higher dimensional base reality. This is because quantum parallelism. A quantum computer naturally handles superposition and entanglement, the core features of our quantum universe, not as bugs to be simulated, but as native hardware operations. Efficiency. Simulating a quantum universe on a classical computer is believed to be exponentially hard. Simulating it on a quantum computer could be vastly more efficient, perhaps even natural. Dimensionality. The holographic principle suggests our 3D time reality emerges from a 2D boundary. This projection could be a computational process occurring in a higher dimensional space that contains both the processor, the boundary, and the projection, our space. The simulation could be run for research, entertainment, or as a natural process. Motivations for running such a simulation are purely speculative. Research, assessor, simulation. As Bostrom suggested, a post-human civilization runs detailed cosmological or historical models of its past. This is the most rational motive. Entertainment, art. An advanced civilization creates immersive experiences or artworks. We could be part of an elaborate game or story. Natural process to physics experiment. The simulation might not be run by conscious beings at all. It could be an emergent, self-organizing process within the base reality's physics, a naturally occurring computational structure that gives rise to conscious substructures, much like our brains naturally arise from biology. The ancestor simulation versus the alien video game scenario. These are two dominant categories of simulation motives. Ancestor simulation, Bostrom. The simulators are Artexantatem, descendants. The simulation is a faithful, or nearly faithful, historical recreation. Its purpose is academic, memorial, or ethical. The rules are our physics, and the timeline is our past. We are meaningful to the simulators. Alien video game, scientific experiment. The simulators are unrelated, advanced aliens, or AIs. We are part of a contained experiment to study consciousness, evolution, or physics. Or we are characters in an entertainment product. The rules might be arbitrarily set, and our existence or suffering is of no more concern to them than the fate of a character in Grand Theft Auto is to a player. This scenario is more existentially unsettling and less constrained by assumptions of fidelity to a real human history. Physics as a discovered source code. This viewpoint reframes the entire scientific enterprise. Instead of discovering Michel laws, physicists are seen as reverse engineering the operating system of reality. Every equation, from Newton's gravity to the standard model Lagrangian, is a piece of decompiled code, revealing the algorithms that govern causal relationships, force interactions, and state changes. The remarkable success of this project suggests we are not just finding patterns in chaos, but uncovering a coherent, rule-based architecture that was instantiated with precision. The Unreasonable Effectiveness of Mathematics in the Natural Sciences, Eugene Wigner. In his famous 1960 essay, Physicist, Eugene Wigner marveled at a profound mystery. Why should a purely human construct of the mind, abstract mathematics, be so perfectly and powerfully adept at describing and predicting the physical world? The predictive power of a mathematical concept often precedes and far exceeds its initial inspiration, e.g., complex numbers in quantum mechanics. This unreasonable effectiveness hints that mathematics is not just a useful tool, but the native language in which the universe is written. In a simulation framework, this makes perfect sense. We are discovering the formal language of the simulation's code. Is math invented or discovered? The Platonic realm argument. This is a central philosophical divide. Invented. Mathematics is a human-made language, a logical game of symbols we project onto the world. Its effectiveness is a happy accident or a result of our brains evolving to recognize patterns. Discovered. Platonism. Mathematical truths, like the properties of prime numbers or pi, exist independently in a timeless, non-physical, Platonic realm. We discover these eternal truths. We do not create them. The simulation hypothesis leans heavily on the Platonist view. It provides a physicalist grounding for the Platonic realm. The mathematical structures exist as an abstract code, logic, in the simulator's framework, before it is executed to generate a physical reality. If math is discovered, it suggests a pre-existing logical structure, a code base. If mathematical truths are discovered, they imply an kabareshiki abi, objective, pre-existing logical architecture. The simulation hypothesis offers a compelling answer to the question, where does this architecture exist? It exists as the coimmutable codebase and rule set. In the simulator's environment, the laws of physics and our universe are a specific, instantiated implementation of this more fundamental, abstract mathematics. We are effectively debugging the program from the inside. The fundamental constants, speed of light, gravitational constant, Planck's constant. These are the Cabet fixed numerical parameters. In the equations of physics, they are not derived from deeper theory. They are measured inputs. Example, irate, c, speed of light. The maximum, processing cha communication speed. G, gravitational constant. Sets the strength of the curvature of spacetime, gravity. A, Planck's constant. Sets the scale of quantum effects, the size of the quanta. In a simulation, these are the hard-coded parameters, set in the initialization file. They define the hardware specs and behavioral limits of the simulated reality. Fine-tuning. The constants are precisely set to allow for complex life. The kara fine-tuning problem is perhaps the strongest empirical hint that something is afoot. Dozens of fundamental constants, like the strength of nuclear forces, the cosmological constant, must lie within an exceedingly narrow range for stars, planets, and carbon-based life to exist. A tiny change in any one would result in a sterile universe of only hydrogen, or one that collapses instantly, or where no atoms form. Example, if the strong nuclear force were 1% stronger, all hydrogen would fuse into helium in the Big Bang, leaving no water or fuel for stars. The anthropic principle as an explanation, verse, as evidence for design simulation. The anthropic principle is the standard counter to fine-tuning. Weak anthropic principle. We can only observe a universe compatible with our existence. If the constants were different, we wouldn't be here to ask the question. This is a selection effect, not an explanation. Strong anthropic principle. The universe must have constants that allow for observers. This is often seen as teleological and unsatisfying. Proponents of the simulation or intelligent design argument turn this on its head. The anthropic principle is not an explanation for fine-tuning. It is the observation that begs for an explanation. A simulated universe provides one. The parameters were selected by chance, design, or experiment from a set of possibilities to produce interesting, complex outcomes like life. Could constants be simulation parameters? Adjustable by the programmer? Absolutely. In a simulation, constants are variables. A programmer could run the simulation with gravity strength, Yauch 0.5, or speed of light, barring $200,000 just as easily. The fact that our universe has a single, immutable set of constants could be a feature of our specific run. This leads to a testable prediction. If we are in a massively multiplayer simulation with different realms, or if the simulation has patches, we might find lacked domains with different physics or variations in constants. The search for variation in constants over time or space. This is a major frontier in experimental cosmology. If constants are truly fundamental and mathematical, they should be immutable. If they are simulation parameters, they might drift, have regional variations, or exhibit quantization. Experiments use astrophysical observations, analyzing light from distant quasars over billions of years, to see if the fine structure constant, AA, has changed. Atomic clocks. Comparing ultra-precise clocks over years to detect drift. Cosmic microwave background. Looking for signatures of different physics in the early universe. Any confirmed variation would shatter the standard model of physics and be explosive evidence for a dynamic, constructed reality. The structure of spacetime. Is it continuous or a lattice? This is the ultimate empirical question for the digital physics view. Continuous, classical relativistic view. Spacetime is a smooth, infinitely divisible fabric. Discrete, lattice, digital, quantum gravity view. Spacetime has a minimum unit, the Planck scale, and may have an underlying geometric structure, like a crystal lattice or a spin foam. If experiments ever find evidence of Lorentz invariance violation, where the speed of light varies slightly with direction or energy, hinting at a preferred lattice structure, it would be a monumental discovery pointing toward a pixelated, computational universe. Current particle physics and gamma-ray burst observations place incredibly tight constraints on such effects. But the search continues at ever higher energies. Loop quantum gravity, spacetime as a network of discrete loops. Loop quantum gravity, LQG, is a major competitor to string theory in the quest to unify gravity and quantum mechanics. It takes the idea of discrete spacetime seriously. In LQG, space is not a background container, but a dynamic woven fabric of finite quantized loops of gravitational field lines. These loops form a network, a spin network, ARC, and the intersections represent the smallest possible volumes, quanta of space. This provides a direct mathematical picture of a pixelated universe, where geometry itself arises from the combinatorial relationships between these fundamental quanta. Spin foams and the granularity of space. Spin foams extend the LQG picture to include time. If a spin network represents quantum space at a given instant, a sabaraba spin foam represents the history, the evolution of that network over time. It visualizes spacetime as a foam-like, discrete structure where the spin network's connections branch and merge. This foam is not made of bubbles, but of fundamental cells of spacetime with Planck scale volumes. This is the most concrete theoretical model of a granular reality, directly implying that smooth geometry is a large-scale approximation of a vast underlying computational process of state changes. Causal dynamical triangulations. Building spacetime from simple geometric pieces, causal dynamical triangulations, CDT, is a powerful computational approach to quantum gravity. It literally builds spacetime from the ground up, using simple fundamental building blocks, tiny triangular Minkowski simplices, 4D generalization of triangles. The simulation runs by letting these pieces randomly connect according to rules that enforce causality, no time travel. Remarkably, from this chaotic soup of simple pieces, a large-scale, smooth, 4D spacetime, like our universe, emerges. CDT is a direct, explicit demonstration of how complex, continuous-looking physics can arise from discrete combinatorial rules, a perfect analog for a universe generated by an algorithm. Evidence for spacetime foam from high-energy astrophysics. Spacetime foam is the hypothetical turbulent, grainy structure of spacetime at the Planck scale, predicted by quantum gravity. While we cannot probe it directly, astronomers look for subtle effects on light traveling across the universe. Gamma ray bursts. Light of different energies from the same distant burst should travel at very slightly different speeds if spacetime is foamy, as higher energy photons stumble more on the granularity. Instruments like the Fermi Gamma Ray Space Telescope have placed extremely tight constraints on this effect. So far, spacetime appears smooth, to within many orders of magnitude above the Planck scale. But the search for any deviation continues as a key test. The speed of light as a cosmic processing speed limit, render rate. In a computational framework, the speed of light, sokeakesikoke, is not just the speed of photons. It is the maximum rate at which information or causality can propagate across the system. This is identical to the concept in computing of a clock speed or bus speed. Kailazerde, the finite speed at which signals travel across a processor to maintain synchronization. Nothing can happen faster than a CKBD because the underlying processor cannot update the state of separated parts of the simulation in a causally inconsistent way. It's the universe's ultimate refresh rate. Special relativity, time dilation, and length contraction as optimization techniques. Einstein's special relativity shows that moving clocks tick slower and moving rods contract. From a simulation perspective, these are not illusions, but necessary computational protocols. To preserve the constancy of Tsoipesifoakisek, the processing speed limit, for all observers, they ensure causality is never violated, no matter the frame of reference. It's an elegant, built-in coordinate transformation code that guarantees the simulation's internal consistency. The fact that the laws of physics look the same to all uniformly moving observers, relativity, is a hallmark of a well-designed, rotationally and translationally invariant code. General relativity, gravity as curvature of spacetime, or a data structure. General relativity describes gravity not as a force, but as the curvature of the smooth, continuous spacetime geometry caused by mass and energy. In a computational quantum gravity view, this geometry is an emergent property of a dynamical data structure. Matter and energy tell the underlying spin network or spin foam how to connect and evolve, and this evolution manifests as what we perceive as curvature and gravitational attraction. Gravity becomes a consequence of the relational dynamics of the universe's fundamental informational bits. The challenge of unifying general relativity and quantum mechanics. This is the central crisis of modern physics. General relativity describes a cosmos on large scales. Spacetime is smooth, continuous, and deterministic. Quantum mechanics describes a subatomic world. It is granular, probabilistic, and inherently uncertain. They are mathematically and philosophically incompatible. Applying quantum rules to gravity leads to nonsensical infinities. This suggests one or both theories are effective approximations of a deeper, unknown theory, the simulation hypothesis as a potential framework for unification. The computational view offers a conceptual path to unification. Both GR and QM are emergent features of a single underlying computational process. Quantum mechanics describes the discrete, probabilistic, and locally processed rules at the fundamental code level. General relativity describes the smooth, deterministic geometric relationships that emerge when that code is run at a massive scale over many computational steps, like the smooth physics that emerges from cellular automata. The tension between them mirrors the tension between a program's source code, granular with conditional logic, and the resulting real-time graphics, smooth, continuous. Quantum field theory, the universe as a field of operators and excitations. Quantum field theory, QFT, is our most successful framework, combining quantum mechanics and special relativity. In QFT, the universe is not empty space containing particles. Instead, it is filled with fundamental quantum fields, exhibit electron field, quark field, photon field. Particles, quanta, are localized excitations or vibrations. In these fields, the fields themselves are described by operators and wave functions. In simulation terms, these fields are the primary data structures. The entire universe is a dynamic, interacting set of fields, and particles are just rendered manifestations of excitations in these fields, with their creation and annihilation governed by strict quantized rules. A perfect description of a processed informational reality. The concept of quanta itself implies discrete packets of something. The word quantum, Latin, how much, is the fundamental rupture from classical physics. It means that physical properties do not vary smoothly, but come in indivisible, discrete units. This applies to energy, photons, angular momentum, electron orbits, electric charge, and the charge of an electron, perhaps spacetime itself, Planck scale. This inherent granularity is the single most compelling evidence for a digital or computational substrate. A continuous, analog reality would have no need for such fundamental chunkiness. Quanta are akin to the bits or pixels dot of reality, the smallest addressable units of information and interaction. Renormalization, the mathematical process of removing infinities from particle physics. In quantum field theory, simple calculations for particle interactions, like electron-electron scattering, often yield nonsensical, infinite results. Renormalization is the ingenious, if seemingly ad hoc, mathematical procedure used to subtract these infinities. It involves introducing counterterms that absorb the divergences, leaving behind finite, exquisitely accurate predictions that match experiments to many decimal places. While spectacularly successful, it feels like a mathematical trick, a workaround rather than a deep principle. Could renormalization be a bug fix for a poorly defined computational model? From a simulation perspective, renormalization appears suspiciously like patching a computational flaw. The infinities could arise because physicists are trying to apply continuous mathematics, calculus, to a system that is, at its core, discrete and finite. The infinities are artifacts of asking the wrong question, e.g., what is the value at a dimensionless point of a pixelated system? Renormalization might be our way of unconsciously correcting for the underlying finite resolution, or the round off errors inherent in the simulation's arithmetic. In this view, we are not fixing our theories, we are approximating the simulator's own internal error correction protocols, symmetries, and conservation laws. Noether's theorem. In 1918, mathematician Emmy Noether proved one of the most profound theorems in physics. It states, for every continuous symmetry of the laws of physics, there is a corresponding conserved quantity. Symmetry means the laws look the same under a transformation, e.g. any joji, moving your lab in space, rotating it, or running an experiment tomorrow. Conserved quantity is something that cannot be created or destroyed, like energy, momentum, or electric charge. Noether's theorem links the beautiful abstract geometry of the universe to the concrete bookkeeping of measurable quantities. Energy, momentum, charge. Conservation as results of underlying symmetry. Noether's theorem gives us the precise origin of our most sacred conservation laws. Time, translation symmetry. Laws are the same today as tomorrow. Conservation of energy. Spatial translation symmetry. Laws are the same here as over there. Conservation of momentum. Rotational symmetry. Laws are the same in all directions. Conservation of angular momentum. Gauge symmetry. A more abstract phase invariance. Conservation of electric charge. This reveals that conservation isn't arbitrary. It's a necessary consequence of the ANM, invariant structure of reality's rule set. In a simulation, conservation laws prevent illegal state changes and save processing power. In computational terms, conservation laws are brilliant optimization and stability protocols. Stability. They prevent catastrophic illegal state changes. You cannot spontaneously create energy from nothing, which would crash or corrupt the simulation state. They enforce causality and order. Efficiency. They allow for local processing. A simulator doesn't need to do a universe-wide check to ensure energy is conserved. It can enforce it as a local rule of every interaction, massively simplifying the computation. Conservation laws are the error checking and memory management routines of the cosmic code. The violation of parity symmetry in a weak nuclear force, a deliberately coded quirk. Most fundamental forces obey powered by parity symmetry. The mirror image of a process is equally valid. In 1956, Chen-Ning Yang and Songdao Li predicted, and Chen Shengwu confirmed, that the EQD weak nuclear force violates parity maximally. A mirror image version of a weak decay simply does not occur in nature. This was a shocking discovery. From a simulation perspective, this could be seen as a deliberate asymmetric rule, written into the code of one specific interaction. It's not a bug, it's a feature that breaks a symmetry, perhaps necessary for generating the matter, antimatter asymmetry that allowed our universe of matter to exist. It shows the rule set has specific nuanced exceptions. The search for a digital substrate, cellular automata, CA, are the simplest and most compelling models for a digital universe. A CA consists of a grid of cells. Each cell has a finite number of states, yi chatwi ji, on dot off, a set of rules, a simple deterministic rule that updates each cell's state based on the states of its neighbors. Discrete time steps. The universe updates in ticks, despite their simplicity. CAs like Conway's Game of Life can produce astonishing complexity, including self-replication and universal computation. They are a proof of concept that simple, local, digital rules can generate a rich, seemingly complex reality. Stephen Wolfram's New Kind of Science and the Universe as a Cellular Automaton. In his controversial 2002 book, physicist Stephen Wolfram argued that simple computational programs, particularly cellular automata, are the key to understanding the universe. He contends that the complexity of nature isn't the result of complex underlying laws, but emerges from the iterative application of very simple rules. Much like a CA, he suggests the universe might literally be a giant CA, with the Planck scale representing the size of one cell. His work pushes the idea that physics is not about equations, but about the computational, irreducible processes generated by such rules. Edward Fredkin's Digital Physics. The universe is a cellular automaton with a finite set of states. Pioneer. Edward Fredkin took this idea to its logical extreme. His theory of digital physics, with finite nature, posits 1. The universe is yet finite. In every regard, finite information, finite states, finite size. 2. The universe is a cellular automaton. Space, time, and matter are all discrete. 3. The underlying mechanics are the deterministic and reversible. No information is destroyed. For Fredkin, particles, forces, and even quantum mechanics are phenomenological approximations of the CA's digital dynamics at a scale much larger than the individual cell. He provided a concrete, if highly speculative, vision of a fully computational universe where it from bit is not a metaphor, but a literal engineering specification. Conway's Game of Life. As a metaphor, simple rules, generating immense complexity. Conway's Game of Life is a canonical, tatum, 2D, cellular automaton, with breathtakingly simple rules based on a cell's 8 neighbors. 1. Survival. A live cell with 2 or 3 live neighbors stays alive. 2. Death. A live cell with fewer than 2, loneliness, or more than 3, overcrowding neighbors dies. 3. Birth. A dead cell with exactly 3 live neighbors becomes alive. From these 3 local deterministic rules emerge gliders, spaceships, pulsars, and even universal Turing machines, structures that can compute anything. This serves as the prime metaphor for the simulation hypothesis. A vast, complex, seemingly living universe can arise from the iterative application of simple, digital, local rules. There is no central controller, only rule execution. From simple rules to emergent phenomena. This mirrors established physics. We do not need a separate law of aerodynamics, programmed into birds. Flight emerges from the interaction of bones, muscles, and air molecules, obeying simple mechanical and thermodynamic rules. Similarly, thermodynamics, heat entropy, emerges from the statistical behavior of countless particles. Fluid dynamics. Turbulence waves emerges from molecular interactions. Chemistry emerges from quantum electrodynamics. The simulation argument asks, could our entire suite of fundamental forces and quantum fields be similarly emergent phenomena arising from a deeper, simpler, perhaps digital layer of rules we haven't yet decompiled? Could our fundamental laws be emergent from deeper, simpler, computational rules? This is the radical proposition. We assume the standard model and general relativity are fundamental, but they could be higher level APIs, approximate effective descriptions that work brilliantly at our energy scales, but are themselves the product of a more primitive, possibly computational substrate. The search for a theory of everything may not be for a more complex equation, but for the simple algorithm, whose long-term behavior manifests as our physics. The challenge is that such underlying rules might be computationally irreducible. We can only discover them by running the simulation, not by pure deduction. Information theory. The universe as a processor of information. Information theory, pioneered by Claude Shannon, provides a mathematical framework for quantifying and transmitting information. Applied to physics, it suggests the universe's primary activity is not matter and energy moving in space and time, but information being processed. Every collision, every quantum measurement, every gravitational wave is viewed as a state change in a vast distributed computation. Reality is a Bafonikakio's cosmic information processing network, with physical laws being the algorithms governing how information is transformed and transmitted. John Wheeler's It from Bit. All physical things are information, theoretic in origin. The late legendary physicist John Wheeler coined this phrase to capture a profound paradigm shift. It refers to every particle, field, and force, the stuff of the physical world. Bit refers to the binary yes, no choices that constitute information. It from Bit proposes that every physical entity ultimately derives its existence from any informational transactions, answers to yes or no questions posed and revealed by quantum measurements. In this view, the universe does not contain information. It is information. Matter and energy are manifestations. Information is the fundamental substance. The thermodynamic cost of erasing a bit of information, Landauer's principle. In 1961, Rolf Landauer made a stunning discovery linking information and physics. Erasing one bit of information in an irreversible computation necessarily dissipates a minimum amount of energy as heat, kBT ln2, where kB is Boltzmann's constant and T is temperature. This isn't an engineering limitation, it's a fundamental law of thermodynamics. Throwing information away increases entropy. This means information is not abstract. It has a UXC, physical, energetic cost. Manipulating information is manipulating the physical world. This links information, processing directly to physics. Landauer's principle erases the Cartesian divide between the abstract world of computation and the concrete world of physics. It shows that computation is a physical process. You cannot build a computer that violates thermodynamics. Physics has an informational character. The minimum energy cost of a logical operation is now a key constraint in physical theories. This two-way street is the bedrock of the physics of information, making the question, is the universe a computer? Not just metaphorical, but technically and theoretically grounded. Black holes as ultimate information. Theorists' puzzles. Black holes are the ultimate stress tests for the it from bit concept. They challenge our understanding of how information relates to space, time, and quantum mechanics. A black hole's properties, mass, charge, spin, seem to offer very little information about what fell in, violating the quantum principle that information is never destroyed. This makes them cosmic laboratories for probing the informational architecture of reality. The black hole information paradox. Is information destroyed? Stephen Hawking's 1974 calculation showed black holes evaporate via Hawking radiation, which appears to be purely thermal, random, featureless. If the black hole evaporates completely, the Yekidera information about all the matter that formed it seems to be lost forever, violating quantum unitarity, the principle that information must be preserved. This is the paradox. For decades, it set gravity, which allows information destruction in black holes, against quantum mechanics, which forbids it. Hawking's later concession: information is preserved. But how? In 2004, Stephen Hawking famously reversed his position, conceding that information does escape from black holes. He was persuaded by developments in string theory and the holographic principle. The current consensus is that information is preserved, but the mechanism remains one of the greatest mysteries in physics. The leading idea is that information is scrambled and encoded in the quantum structure of the event horizon and then slowly radiated out in subtle correlations within the Hawking radiation. Solving how this happens is believed to be the key to unlocking quantum gravity. The paradox itself cemented the idea that information is the most fundamental currency in the universe. The holographic solution: information is encoded on the event horizon. The holographic principle resolves the black hole information paradox by radically redefining where information lives. It states that all information about everything that has ever fallen into a black hole is not lost inside the singularity, but is entirely encoded on the black hole's event horizon. The 3D volume of the black hole is a keener projection of this 2D data. When Hawking radiation is emitted, it carries this information away via subtle quantum correlations, preserving it. This isn't a metaphor, it's a specific mathematical consequence of quantum gravity. Models like string theory's ADS CFT correspondence. This is a literal example of a data compression and storage scheme in nature. The holographic mapping is nature's ultimate lossless data compression algorithm. It compresses a three-dimensional volume of spacetime, including all the complex matter within it, onto a two-dimensional surface. The resolution of the hologram is set by the Planck area. This is directly analogous to how a 3D Blu-ray movie is stored as 2D data on a disc and then decoded by a player to project a 3D image. The universe appears to employ the same engineering principle, storing information in the most efficient possible way, which for gravitational systems is on a boundary, not within a volume. Quantum computing and the simulation. Could our universe be running on a quantum computer in a base reality? This is the most compelling speculation for the hardware of a simulation, simulating a quantum mechanical universe. On a classical computer is believed to be exponentially difficult, requiring impossible amounts of resources. However, a Seum quantum computer in the base reality could simulate our quantum universe natively and efficiently. Our universe's core features, superposition, entanglement, and interference, would not be laboriously calculated but would emerge naturally as features of the parent quantum computer's own operational logic. It's the difference between simulating water molecule by molecule and just having a pool of water. The concept of quantum supremacy, solving problems. Classical computers. Cannot quantum supremacy or quantum advantage is the point where a quantum computer performs a specific, well-defined calculation faster than any feasible classical supercomputer. This has already been tentatively achieved, e.g., by Google in 2019. The concept shows that in quantum and classical computation are fundamentally different paradigms. If a base reality civilization wanted to create a richly quantum simulated universe, achieving quantum supremacy would be a prerequisite. It underscores that the computer running our universe is likely not classical. If our universe's quantum weirdness requires a quantum computer to simulate, it places limits on the parent universe. This logic leads to a profound constraint. The parent universe, base reality, must have at least the computational complexity of a universal quantum computer. Its laws of physics must support quantum computation. This argues against the idea of a simple classical machine in a garage. It suggests the base reality is at least as complex and quantum as our own, if not more so. It also implies that nested simulations, see point 86, would have to run on progressively less powerful or more abstracted hardware, potentially imposing a limit on how many layers deep a simulation stack can go before resources are exhausted. 6. The simulation could be nested simulations within simulations. If an advanced civilization can run one high-fidelity simulation containing conscious beings, those simulated beings could eventually develop their own technology and run their own sub-simulations. This leads to a potential infinite regress of simulations within simulations. In such a scenario, the probability of being in the original base reality becomes vanishingly small, as simulated realities would vastly outnumber the original. This is a statistical extension of Bostrom's argument. However, each layer likely requires a fraction of the computational resources of the layer above it, imposing a practical limit to the recursion depth. The processing power required to simulate every particle, the naive computational cost is mind-boggling. Simulating every fundamental particle, 1080 in the observable universe, interacting via quantum fields at Planck time resolution, 10 to the 44s, would require resources exceeding those of the universe itself. A logical absurdity. This quantum planetarium argument is a major objection. It forces one of two conclusions. 1. The simulation is not of that fidelity, or 2. The simulation uses profound optimizations that make the task not just feasible, but perhaps natural for the substrate of the base reality, e.g., a quantum computer. The optimization argument. Simulators would only render what is observed, quantum mechanics. This is the most powerful answer to the processing power objection. Quantum mechanics itself provides the blueprint for the ultimate optimization. The simulator does not need to calculate the definite state of every particle. It can use the Poiseuille's wave function, a compressed probabilistic representation of possible states. Only when a measurement-to interaction occurs, a query that requires a definite result, does the system render a specific outcome, a process we call wave function collapse. This just-in-time rendering is analogous to a video game engine that only calculates the detailed physics of objects within a player's field of view. Our entire universe could be run on vastly less power if it's computed this way. The coarse graining of distant or complex systems. Beyond quantum mechanics, the simulation could employ other optimizations familiar from computer science. Level of detail, LOD, distant galaxies, or complex molecular systems are not simulated particle by particle. They are represented by statistical or approximate models. Thermodynamics, fluid dynamics. This is coarse graining. We see this in nature. We don't need quantum chemistry to describe the flow of a river. Encapsulation and hierarchy. Complex structures, atoms, cells, organisms, emerge from simpler rules and are then treated as functional units, reducing the need to recompute their internal dynamics from scratch every time. Cosmic censorship, hypotheses, nature hides, singularities, like a program, hides crashes. In general relativity, singularities, like at the center of a black hole, are points where density and curvature become infinite and the laws of physics break down. Roger Penrose's cosmic censorship hypothesis proposes that nature always clothes these singularities within an event horizon, preventing their infinite weirdness from affecting the outside universe. From a computational view, this is a critical error handling protocol. A singularity is like a binary division by zero error, or a system crash in the code. The event horizon acts as a Hibaka, firewall, or exception handler, containing the crash so the rest of the simulation, the external universe, can continue running stably without being corrupted by the undefined state. What would a glitch in the matrix actually look like scientifically? Contrary to sci-fi visual stutters, a scientific glitch would not be subjective or hallucinatory. It would manifest as a statistically significant, reproducible anomaly in high-precision data, collected by instruments like particle colliders, telescopes, or atomic clocks. It would be an effect that stubbornly resists all conventional explanations within the established frameworks of the Standard Model and general relativity. It would look less like a flying vase and more like a particle track with an impossible energy signature or a pattern in the cosmic background radiation that defies standard inflationary cosmology. It would be a statistical or physical anomaly, inconsistent with our known laws. A true glitch is defined by its reductivity, irreducibility to known physics. It would violate a foundational principle like Lorentz invariance, the laws of physics changing slightly depending on direction or velocity. Conservation laws, energy or momentum not being conserved in ultra-precise experiments. Cosmological isotropy, the universe looking fundamentally different in one direction versus another on the largest scales. The anomaly would have to be so robust that the only alternatives are revolutionary new natural physics, or an artifact of a constructed system. The axis of evil in cosmology, an unexpected alignment in the cosmic microwave background. One of the most discussed potential glitches is the so-called axis of evil. This refers to several unexpected large-scale alignments found in the temperature fluctuations of the cosmic microwave background, CMB. The oldest light in the universe, emitted 380,000 years after the Big Bang. Specifically, the low-order multiples, the largest patterns on the sky, appear to be aligned with each other, and curiously, with the plane of our solar system. This suggests a preferred direction. In the cosmos, which violates the cosmological principle, the bedrock assumption that the universe is homogeneous and isotropic. the same in all places and directions on large scales. The CMB as the afterglow of the Big Bang, the universe's first rendered frame. The CMB is not just ancient light. In computational terms, it is the first fully rendered frame of the observable universe. Before this moment, the universe was an opaque plasma of particles and radiation, too hot and dense for light to travel. As it cooled, protons and electrons combined into atoms, allowing photons to stream free. The pattern imprinted on the CMB is a 2H snapshot of the density fluctuations. At that precise moment, these fluctuations are the seeds of all future cosmic structure, galaxies and voids. Analyzing the CMB is like analyzing the initial conditions and random seed of the cosmic simulation. The alignment suggests a preferred direction, breaking cosmological assumptions. The power of the axis of evil as a glitch is that it challenges the Copernican principle in its most extreme form. Not only are we not at the center of the universe, but there should be no center or special direction at all. The alignment, if real, would imply our location or perspective has a privileged relationship to the universal structure, which is deeply unsettling to standard cosmology. It's as if the simulation's coordinate system or initialization geometry is faintly visible in the data. Mainstream explanations, systematic errors, foreground effects. The strong preference of cosmologists is to explain the axis of evil as an abawit artifact, not a discovery. Leading explanations include galactic foreground contamination, unsubtracted emission from dust or magnetic fields in our own Milky Way galaxy could be imprinting a directional pattern, observational systematics, subtle biases in the way satellites like WMAP and Planck scan the sky could create spurious correlations. Statistical fluke, a posteriori selection. We have mined enormous CMB datasets. Finding a few unlikely patterns in a massive search is statistically expected. The axis of evil, name itself, given after its discovery, highlights this concern. Most cosmologists believe it will vanish with more precise data or better foreground modeling. The simulation argument: could it be an artifact of the simulation's geometry or initialization? If the anomaly persists, the simulation hypothesis offers a distinct class of explanation. The alignments could be a boundary effect, evidence that our universe is a simulation running in a finite container with a specific geometry, like a 3 torus or a cube, whose symmetry axes leave an imprint. An initialization artifact, a fingerprint of the pseudorandom number generator, or the initial state vector used by the simulator to set up the Big Bang's density fluctuations. Correlations in the seed could propagate to the largest scales. A rendering artifact, a subtle sign of the simulation's underlying lattice or computational grid, becoming apparent on the very largest scales where the simulation's coordinate system is barely visible. The cosmic void, the cold spot in the CMB. Another prominent anomaly is the Sawai CMB cold spot, a region in the constellation Eridanus that is unusually large and cold, about 70 microkelvins colder than the average. It is a larger and colder than standard inflationary models easily predict. It stands out as a significant blob in the otherwise statistically uniform CMB map. Is it a supervoid or a texture defect in the early universe's structure? Mainstream astrophysics has proposed two primary natural explanations. 1. The supervoid hypothesis. A gigantic underdense region of space, a void, along the line of sight could cause the CMB photons to lose energy as they travel through it. The integrated Sachs-Wolf effect, creating a cold spot, some large, but perhaps not large enough. Voids have been found in that direction. 2. A cosmic texture, a topological defect, a remnant kink in spacetime fields from a phase transition in the very early universe, could have imprinted the cold spot directly on the CMB. The debate continues because the observed supervoids seem insufficient to explain the cold spot size and coldness fully as a simulation artifact, a rendering error, or a region with different initial parameters. From a simulation perspective, the cold spot could be interpreted as a rendering glitch, a localized error in the computation of the early universe's physics, a cosmic typo in the density field that propagated forward. Think of a corrupted texture in a video game, a patch boundary, evidence of a multi-patch simulation where our universe is stitched together from different computational domains. The cold spot could be a subseam op, where two slightly different simulation volumes with marginally different parameters, like initial density, were joined, creating a discontinuity. A debugging region, a section of the simulation where the programmers altered a parameter, like the dark energy density, to test its effects, leaving an observable artifact. Like the axis of evil, it remains an intriguing mystery that is more likely of natural origin, but its persistence keeps the door open to more speculative interpretations. Particle physics anomalies. Muon G2. Experiments at Fermilab. The Muon G2, G-2, experiments at Fermilab is one of the most sensitive probes for physics beyond the standard model. It measures a fundamental property of the muon, a heavier cousin of the electron, its magnetic moment. The G factor describes how a particle responds to a magnetic field. The experiment isolates muons in a pristine magnetic storage ring and observes how they wobble, precess, as they decay. The measured magnetic moment of the muon disagrees with standard model predictions. The result is a persistent and statistically significant discrepancy between the exquisitely measured value from the experiment and the theoretical prediction from the standard model. The muon's magnetism is slightly stronger than the equations say it should be. This deviation, measured in parts per billion, suggests that virtual particles popping in and out of existence around the moon, which contribute to its magnetic moment, include types not accounted for in the standard model. It is a direct hint of unseen forces or particles. This could be new physics, new particles, or a subtle miscalculation in the code. Mainstream physics fervently hopes this is evidence of Kamakin new physics, such as supersymmetric particles or dark photons. However, the simulation lens offers a different, more subtle interpretation. It could be a Kamui rounding error or approximation artifact in the simulation's calculations. The standard model prediction is the result of humanity's decompiled code, our most accurate mathematical model. The experimental result is the executed output. The discrepancy might indicate that the simulator's internal calculation of quantum vacuum fluctuations, the virtual particle soup, uses a slightly different algorithm or precision level than our derived mathematics. It's not a bug in our universe, but a sign that our reverse engineered model isn't a perfect match for the simulator's native code. The lithium-7 problem in Big Bang nucleosynthesis, Big Bang nucleosynthesis, BBN, is the process in the first 20 minutes of the universe that forge the lightest elements, hydrogen, helium, and trace amounts of lithium and beryllium. Our models of BBN, based on well-understood nuclear physics and the measured density of ordinary matter, make precise predictions. They match the observed abundances of hydrogen and helium spectacularly well, which is a pillar of the Big Bang theory. However, there is one glaring exception: lithium-7. The observed amount of lithium is about 3 times less than predicted. Astronomers measure the abundance of lithium in the atmospheres of ancient stars, which preserve primordial material. The observed value is consistently a factor of 3 to 4 lower than the BBN prediction. This is the lithium problem. It's not a small margin of error. It's a major failure of an otherwise supremely successful model. A bug in the nuclear physics parameters of the early universe. Simulation. From a simulation standpoint, this is intriguing because it's a specific, isolated failure in a precise subroutine. Nucleosynthesis that otherwise works perfectly. It suggests a possible off by 1 error, or an incorrect constant in the nuclear reaction rates for processes involving lithium-7. Perhaps the cross-section probability for a reaction that destroys lithium-7 was set too low, or one that creates it was set too high in the simulation's initial parameters. It's the kind of specific, localized inconsistency that could arise from a programming oversight and an otherwise flawless cosmic code. The Flyby anomaly. Spacecraft gaining unexpected speed. During Earth flybys, a puzzling effect has been observed with several spacecraft, like Galileo, Rosetta, and NEAR, performing gravitational slingshot maneuvers around Earth. Precise Doppler tracking showed they experience tiny, unexplained increases in speed, a few mms after their closest approach, not accounted for by standard gravitational models. This is the flyby anomaly. The effect is small but systematic and repeated. Possible conventional explanations versus a gravitational approximation error in the code. Conventional explanations have focused on subtle, unmodeled effects, atmospheric drag, radiation pressure, or errors in Earth's gravity field models. Some have been partially resolved, but a residual puzzle may remain. From a simulation perspective, this could be interpreted as a Caudy numerical integration error in the simulator's gravity engine. When a fast-moving object interacts strongly with a complex, rotating gravitational source, Earth, the simulation's approximations for calculating trajectories might produce a tiny, consistent discrepancy, a rounding error in the physics engine that only manifests in very specific dynamic conditions. The Pioneer anomaly, now largely explained by thermal radiation, but a lesson in seeking glitches. For decades, the Pioneer anomaly was the gold standard for a potential physics glitch. The Pioneer 10 and 11 spacecraft exhibited a tiny, constant sunward acceleration, about 8.74 x 10 sub 10 tabelio 2, that had no explanation. It fueled speculation about modified gravity or simulation artifacts. After years of painstaking analysis, the consensus is that it was caused by anisotropic thermal radiation. Heat from the spacecraft's radioisotope thermoelectric generators, pushing asymmetrically against the craft. This case is a crucial lesson. Extraordinary anomalies demand exhausting all possible ordinary explanations within the known code, physics, before invoking a glitch. It shows the rigorous process required. Quantum randomness. Is it truly random? This is the deepest question. Quantum mechanics is fundamentally probabilistic. The decay of an atom or the result of a spin measurement is random, with only probabilities given by the wave function. But is this randomness fundamental, true, irreducible randomness in nature, or Kelbidei pseudo-random? Pseudo-randomness. In computing, random-looking numbers are generated by deterministic algorithms from a seed value. If you know the seed and algorithm, the sequence is perfectly predictable. If our universe is a simulation, quantum randomness could be high-quality pseudo-randomness generated by the simulator's algorithm. The seed would be the initial conditions of the Big Bang. This would mean the universe is deterministic at the base level, but unpredictable to us because we lack the seed and algorithm. Experiments testing for hidden variables, like Bell tests, have ruled out local hidden variables, but not non-local or superdeterministic ones, leaving a tiny philosophical crack open for a pseudo-random universe. Proving it's truly random or not may be impossible from within the system. Tests for hidden variables. Bell's theorem violations. The quest to determine if quantum randomness is real or the product of a deterministic underpinning led to Bai. Bell's theorem. 1964. It provided a way to test identity local hidden variable theories. LHVT. The idea that particles have predetermined hidden properties that locally influence their behavior, making outcomes only seemingly random. Bell derived an inequality that any LHVT must obey. Quantum mechanics, however, predicts violations of this inequality due to Sakid-Aki entanglement. Exquisitely precise experiments, notably by Alain Aspect and others, have consistently violated Bell's inequality, ruling out local hidden variables. This is a cornerstone finding. It proves that quantum correlations are non-local, and that the randomness is not due to missing local information. If randomness is algorithmic, pseudo-random, it would leave statistical signatures. While local hidden variables are ruled out, a Sprecium's global deterministic pseudo-random number generator, PRNG, could still underlie reality. In this superdeterministic or simulation model, the entire cosmic history is a single predetermined computation. However, all PRNGs, no matter how complex, have periods and subtle statistical patterns before they repeat. Finding such patterns in ostensibly random quantum events would be a smoking gun. For example, if the random outcomes of trillions of quantum measurements exhibited a non-random, compressible pattern when analyzed on a cosmic scale, it would suggest an underlying algorithm. The challenge is that the seed is the Big Bang, and the algorithm is the universe's laws. Detecting a pattern may require a God's eye view of the entire cosmic data stream. Efforts to find patterns in digits of fundamental constants or quantum random. Number generators. Some researchers have undertaken cosmic numerology key searches, analyzing the decimal expansions of fundamental constants, like the fine structure constant A, for anomalous patterns, repetitions, or evidence they are mathematical constructs, like P or E. More scientifically, physicists continuously test quantum random number generators, QRNGs, devices that use quantum processes, e.g., photon detection, to produce randomness. They subject their outputs to rigorous statistical suites, like the NICE tests, to verify no hidden patterns exist. So far, quantum randomness passes all tests for statistical randomness. Any future failure in a well-shielded QRNG would be a seismic event, potentially indicating an external deterministic influence or a flaw in the randomness subroutine. The nature of consciousness The hard problem. Philosopher David Chalmers coined the term to separate the easy problems of consciousness, explaining attention, reportability, integration of information, from the hard problem. Why and how physical processing in the brain gives rise to faritericaus, subjective experience. Qualia, the redness of red, the pain of a headache. Neuroscience can map correlates of consciousness, but it cannot explain why such processing is felt. This explanatory gap is the central mystery of mind and reality. The simulation hypothesis must grapple with this. Is consciousness simulated, or is it the one real thing interfacing with a simulation? Is consciousness a fundamental feature of the universe or an emergent property? This is the core philosophical divide. Emergentism. Consciousness is a complex property that emerges from specific, sophisticated information processing, like in brains. It is not present in fundamental physics. Panpsychism or fundamentalism. Consciousness is a kitty, fundamental property of reality. Like mass or charge, it may be ubiquitous at a low level, panpsychism, or a feature of certain physical structures, integrated information. The simulation hypothesis can accommodate both, but they lead to very different implications for the simulators and our own nature. In a simulation, consciousness could be a separate process interfacing with the avatar. This is a modern, high-tech version of Cartesian dualism. The body-brain is a simulated avatar, a complex, physics-based puppet within the simulation. Consciousness, or the self, is a such non-simulated external process, garanzamike a player, or soul in the base reality, that is mighty, streaming its experience into and receiving sensory data from the avatar via an interface. This resolves a hard problem by externalizing consciousness. It also explains the ghost in the machine feeling and raises questions about what happens if the interface is disrupted. See near-death experiences. The observer effect in quantum mechanics. Revisited, consciousness causing collapse. The orthodox Copenhagen interpretation is agnostic on what constitutes an observation, but some interpretations, like Ebelin von Neumann-Wigner, propose that Akane consciousness itself is the ultimate cause of wave function collapse. In a simulation framework, this takes on a literal meaning. A conscious observation is the point where the simulation's processor commits to a specific rendered outcome to maintain a consistent, shared reality for that conscious agent. The conscious observer isn't creating reality, but is the Yaxos trigger for a high-fidelity rendering process that resolves quantum probabilities. This makes consciousness not a passive epiphenomenon, but an active, integrated component of the simulation's runtime engine. Integrated information theory, IIT, and panpsychism as potential clues. Integrated information theory, IIT, developed by Giulio Tononi, is a leading scientific theory of consciousness. It proposes that consciousness corresponds to a system's phi, a mathematical measure of its capacity for integrated information. A system has consciousness to the extent it can differentiate and integrate information in a unified way. This theory has a panpsychist flavor. Where there is integrated information, there is some form of experience. In a simulation, IIT could be seen as identifying the computational structures that qualify for user access or rendering privileges. High-F systems, like brains, are complex enough to host a stream of consciousness from the base reality, whereas low-F systems, a thermostat, are not. Near-death experiences and altered states. Reports of seeing the code or the framework. Anecdotal reports from deep psychedelic experiences, meditation, or near death experiences, NDEs, sometimes include visions of reality as a geometric lattice, a flowing tapestry of symbols, or a digital construct. People report seeing the matrix or understanding reality as an information process, while neuroscience explains these as brain states under stress or chemicals, like DMT, from a simulation perspective. They are tantalizing. Could these states represent a temporary glitch in the interface or a debug mode where the underlying data structures or rendering processes of the simulation become partially visible to the conscious user? It's the ultimate untestable anecdote, but it persists in the lore. Déjà vu as a potential memory buffer, error, or timeline synchronization glitch. Déjà vu, already seen, is the eerie feeling that a current experience has happened before. Neuroscience typically attributes it to a minor neurological hiccup, a brief delay in processing sensory information into long-term memory, causing the brain to mislabel the now as a memory. In a simulation framework, more exotic explanations arise. Memory buffer. Error. A temporary fault where a current perception is incorrectly written to or read from the memory cache for past experiences. Timeline synchronization. Glitch. In a complex, branching, or multi-threaded simulation, a feeling of déjà vu could be a fleeting awareness of a similar or parallel timeline where the event did occur. It's a momentary desynchronization or crosstalk between closely related world lines. While the neurological explanation is sufficient, the simulation analogy provides a vivid computational metaphor for the subjective experience. The Mandela effect, false memories, or retroactive changes. The Mandela effect refers to a situation where a large group of people shares a detailed, specific memory that contradicts documented reality, e.g., remembering Nelson Mandela dying in prison in the 1980s, or the Berenstain Bears being spelled Berenstein. The mainstream explanation is psychological. False memories, arising from confabulation, social reinforcement, and the malleability of human memory. From an extreme simulation perspective, however, proponents suggest it could be evidence of retroactive changes to the simulation's database, a patch or update that alters some historical or trivial datum, like a logo, leaving a residue of the old data in the memory of some users. This is scientifically untenable as it's unfalsifiable, but it exploits a genuine curiosity about collective memory. Critically analyzing pop culture. Glitches. Most phenomena cited as glitches, déjà vu, coincidence, visual oddities in photos, have well understood psychological, perceptual, or technical explanations. Our brains are pattern matching machines prone to apophenia, seeing meaningful patterns in random noise. Camera sensors produce artifacts. Memory is reconstructive, not photographic. Citing these as evidence for a simulation commits a classic fallacy of personal incredulity. I can't explain this, therefore it must be proof of a simulation. This approach lacks the rigor required for a scientific hypothesis. The importance of rigor, not every coincidence is a glitch. The simulation hypothesis gains traction only when it engages with quantifiable statistical anomalies at the limits of precision measurement. Like the Mauen GE2 discrepancy or the CMB cold spot. These are phenomena that resist explanation even after exhaustive conventional analysis. Elevating every personal coincidence or memory quirk to the level of cosmic evidence dilutes the argument into fantasy and guarantees dismissal by the scientific community. Rigor demands that a potential glitch must be 1. Measurable, 2. Reproducible, and 3. Inconsistent with all standard models to a high degree of statistical significance. UFO UAP phenomena as potential NPCs or player characters. This is a highly speculative but culturally resonant angle. If our universe is a simulation, unidentified anomalous phenomena, UAP, could be interpreted as NPCs, non-player characters, automated probes or entities programmed to interact with or observe the simulation's environment, us, for data collection or system monitoring. Their seemingly physics-defying maneuvers could be exploits or admin privileges within the simulation's physics engine. Player characters. Avatars controlled by entities from the base reality, the programmers or other users, visiting or interacting with the simulation. Their erratic behavior could reflect unfamiliarity with or testing of the simulation's rule set. This frames UAPs not as extraterrestrial, but as phenomena internal to the simulation's operational or social structure. This is a highly speculative but culturally relevant angle. The recent shift in official discourse around UAPs, coupled with the popularity of simulation theory, has created a cultural convergence. It provides a modern technological mythology to explain high strangeness reports that resist conventional prosaic weather balloons, secret tech, or extraterrestrial explanations. While it captures the imagination, it currently resides firmly in the realm of a speculative fiction due to a lack of hard, publicly available physical evidence that meets scientific standards. The scientific community's justifiable skepticism toward such claims. Scientists are rightly skeptical for foundational reasons. Extraordinary claims require extraordinary evidence. Sagan Standard. Proposing that UAPs are simulation artifacts is an extraordinary claim. The evidence provided so far is largely anecdotal, blurry, or classified, failing to meet the extraordinary threshold. Methodological naturalism. Science operates on the principle that phenomena have natural explanations. Jumping to a simulation artifact explanation is a Ba'athy science stopper. It halts the productive search for physical within-universe causes, e.g., novel atmospheric plasmas, sensor spoofing. Falsifiability. The simulation NPC idea is currently unfalsifiable. It can explain anything and predicts nothing specific, making it a pseudoscientific notion in its current form. The Fermi paradox. Where is everybody? Enrico Fermi's famous question highlights the contradiction between the high probability of extraterrestrial civilizations, given the age and size of the universe, and the complete lack of evidence for them. If life is common, why have we not seen or heard from anyone? This paradox remains one of astronomy's great unanswered questions. Simulation explanations. The zoo hypothesis, or simulation isolation. The simulation hypothesis offers fresh takes on classic Fermi paradox solutions. The zoo hypothesis, simulation edition. We are in a contained simulation, or zoo, designed for observation. The programmers have isolated our region of the simulation or imposed a prime directive, preventing other simulated civilizations or themselves from making contact to preserve the integrity of the experiment. Simulation, isolation. We might be the only conscious civilization in this particular simulation run, making the paradox moot. or FTL travel tow communication might be fundamentally disabled in the code as a simplifying rule to reduce computational overhead. The Great Filter as a simulation. Reset or quarantine protocol. The Great Filter is a hypothesized event or barrier that prevents life from progressing to interstellar civilization. In a simulation context, the filter could be a deliberate feature. Reset protocol. If a simulated civilization reaches a certain technological threshold, e.g., capable of altering the simulation itself or becoming a threat to its stability, the simulation is reset or terminated. This could explain why we see no old galaxy-spanning civilizations. Quarantine trigger. The development of, say, artificial general intelligence or self-replication might trigger a quarantine subroutine that prevents further expansion or communication, effectively acting as a filter. We may be approaching our own filter, distinguishing between creative speculation and testable science. This is the crucial final step. The simulation hypothesis exists on a spectrum. Creative speculation, metaphor. A powerful philosophical and narrative framework for reinterpreting mysteries, UAPs, Fermi paradox, consciousness. It generates intriguing what-if scenarios. Testable scientific hypothesis. A narrow technical claim that makes unique, falsifiable predictions about observable reality, e.g., evidence of a space-time lattice, anomalies in quantum randomness, specific patterns in CMB data, not predicted by inflation. The hypothesis only earns scientific credibility by moving from the first category to the second. Its value lies not in explaining pop culture glitches, but in motivating ultra-precise tests of fundamental physics that could, in principle, reveal the informational and computational fabric of reality, whether it is simulated or not. Can the simulation hypothesis be falsified? A key requirement for science. For the hypothesis to be considered scientific, and not just philosophical speculation, it must make a specific testable predictions that could, in principle, prove it false. This is the principle of falsifiability. Karl Popper. A vague claim like "we are in a simulation" is not falsifiable. However, a more precise claim, such as "our universe is a simulation running on a discrete space-time lattice with specific properties," can generate concrete predictions about observable phenomena. The scientific endeavor shifts from asking, "Are we in a simulation?" to, "If our universe has a computational substrate, what observable signatures would that leave?" Proposed experiment by Silas R. Bean and team. Latest QCD simulation. In a seminal 2012 paper, physicist Silas R. Bean and colleagues proposed a concrete test. They noted that when physicists simulate complex quantum systems, like the strong nuclear force, on classical computers, they must approximate continuous spacetime with a discrete 3D cubic lattice. This technique is called lattice quantum chromodynamics, lattice QCD. They reasoned that if our universe is a similar lattice simulation, it would likely also use a cubic lattice as its most efficient and simple computational grid. This underlying grid would impose subtle directional anisotropies on physical phenomena. If our universe is a lattice simulation, cosmic rays would have a specific directional bias. The key prediction is this: an underlying cubic lattice would break. Rotational symmetry. Isotropy. High energy particles moving through this lattice would not behave identically in all directions. Their interactions, specifically the scattering of ultra-high energy cosmic rays, off the cosmic microwave background radiation would be Hertz suppressed along the primary axis of the lattice. This is because along the axis, the possible momentum states of particles are more restricted, a phenomenon seen in all computer lattice simulations. Thus, we would observe a directional cutoff or a lack of cosmic rays from specific symmetry-aligned directions in the sky. Details of the proposed test using the GZK cutoff for high-energy cosmic rays. The test leverages the Grayson-Zatsepin-Kuzmin GZK cutoff. This is a predicted limit on the energy of cosmic ray protons from distant sources, caused by their interaction with CMB photons. They scatter via the plus resonance. In a lattice simulation, this scattering process would be modified. Bean's team calculated that the angular distribution of the most energetic cosmic rays above 1019 eV would show a clear cubic symmetric pattern, revealing the axis of the simulation's grid. This pattern would be a smoking gun for a discrete, constructed spacetime. Current observational limits and future detectors. Needed current observatories like the FARCAM, Pierre Auger Observatory, Argentina, and the Soxhadikiko Telescope Array, Utah map, high energy cosmic rays. Their data so far shows no evidence of the predicted cubic lattice anisotropy. The universe appears isotropic at these energies. This places a lower limit on the Baakika scale of any possible underlying lattice. It must be finer than the scale these cosmic rays can probe, roughly 10 to 12 meters, far above the Planck scale. To probe a Planck scale lattice, 10 to 35 mirror, we would need cosmic rays with energies trillions of times higher than currently observed, which is likely impossible. However, the test remains valid. It is a falsifiable prediction that has, so far, yielded a null result, constraining one specific version of the simulation hypothesis. Testing the holographic principle with quantum gravity. Experiments. The holographic principle is a mainstream theoretical concept in quantum gravity. Testing it is a direct way to probe the informational nature of spacetime. Experiments aim to detect signatures that spacetime is not fundamental 3D, but a by projection from a 2D information layer. This could involve looking for quantum fluctuations of spacetime itself that match holographic predictions, using laser interferometers to detect holographic noise at the Planck scale. The idea is that if spacetime is fundamentally pixelated or holographic, it should have a fundamental jitter or noise at the Planck scale. This holographic noise would manifest as a fundamental limit to the precision of any length measurement. Laser interferometers, like LIGO but built for this specific purpose, can search for this by looking for correlated, non-random noise in their arms that cannot be attributed to seismic activity, thermal noise, or quantum shot noise. 138. The holometer experiment at Fermilab. Its goals and null results. So far. At the holometer. Holographic interferometer at Fermilab was a dedicated experiment to detect this Planck scale holographic noise. It used two powerful co-located Michelson interferometers to look for Yipao correlated jitter tone in their laser beams that would indicate a shared fluctuation of spacetime itself. After collecting data, the analysis published in 2015 found no evidence of holographic noise. At the scale it was sensitive to, down to about 10 hours after 18 meters, still far from the Planck scale. Like the cosmic ray test, this was a null result, but it falsified specific models. that predicted noise at an accessible level, pushing the possible scale of any holographic graininess even deeper. Looking for computational signatures in the CMB's statistical properties. This is a more general data mining approach. If the universe's initial conditions were generated by a finite digital process, a simulation's PRNG, the pattern of fluctuations in the CMB might contain subtle statistical signatures. These could include non-Gaussianities. The standard inflationary model predicts CMB fluctuations are nearly perfectly Gaussian, random. Specific, unusual forms of non-Gaussianity could hint at algorithmic generation. Low-order correlations, unexpected correlations or repetitions on the largest scales beyond the axis of evil could suggest a finite, periodic, or crystallographic underlying structure to the simulation's initial state vector. Searching for repeating patterns or correlations that suggest a finite, cyclical, underlying process. A finite simulation running in a finite computer would have limits. If the simulation's memory or processing is finite, the universe might exhibit large-scale periodicity or correlations that hint at a finite world size or a cyclical process. Astronomers already search for such signs, like a repeating pattern in the large-scale distribution of galaxies, to test if the universe is finite and has a multiply-connected topology, like a 3 torus. Finding such a structure wouldn't prove a simulation, but it would be consistent with a finite constructed environment, much like the periodic boundary conditions used in computational models. Hidden variables. It leaves open the possibility of superdeterminism, a deterministic universe, where everything, including our random, experimental choices, is predetermined. Some researchers propose ultra-precise, loophole-free Bell tests with even greater separation and faster measurement to further constrain any conceivable hidden variable model. Others look for patterns in the random outcomes of trillions of quantum measurements from experiments around the world, searching for subtle global correlations or deviations from perfect randomness that might hint at an underlying deterministic algorithm with a cosmic scale cycle. Proving true, fundamental randomness is incredibly difficult. Finding even a hint of determinism would be revolutionary. Large-scale quantum computer experiments. Can we create a baby universe simulation? This is the ultimate material test. As quantum computers scale up, we could attempt to simulate quantum field theories or simple models of spacetime, like spin foams or causal sets, with increasing fidelity. The goal would not be a conscious universe, but to see if the simulated physics naturally gives rise to emergent phenomena that mirror our own, like simulated Hawking radiation from a simulated black hole, or the emergence of geometric spacetime from pure information. Success would be a proof of concept that a universe with laws like ours can emerge from information processing. If we can create such a toy universe, it powerfully demonstrates the principle that our own universe could be one. The ethical implications of creating a conscious simulation. If a simulation ever advances to the point of containing self-aware, suffering, or joyful entities, it creates staggering ethical dilemmas. Rights of simulated beings. Do they have moral standing? Is it ethical to shut down the simulation, effectively committing genocide? Purpose and suffering. Would creating a simulation with pain and injustice like ours be inherently unethical? Consent. Simulated beings cannot consent to their existence. This is a direct parallel to debates about artificial general intelligence, AGI rights, but with the added layer that these beings would inhabit a world entirely of our making. It suggests any advanced civilization capable of such simulation must develop a strong simulation ethics, potentially with strict rules against creating conscious simulations. If we become simulators, it drastically increases the odds we are in one. This is the recursive core of Bostrom's statistical argument. If humanity survives and develops the capability to run many high-fidelity ancestor simulations, we become the impossibly post-humans. In the trilemma, our very act of creating such simulations would provide strong inductive evidence that other civilizations in our universe's history likely did the same. Therefore, the number of simulated realities would begin to dwarf the number of base realities. By becoming simulators, we would effectively be gambling that we are not in the unique original base reality, because the odds would statistically shift against it. Our technological success becomes a potential indicator of our own simulated nature. The technological trajectory, from pixelated graphics to photorealistic VR. The historical trend is undeniable. In 50 years, we've gone from Pong to immersive VR and photorealistic CGI. Extrapolating this trajectory over centuries or millennia suggests that creating immersive, interactive virtual environments indistinguishable from physical reality is a plausible technological endpoint. The gap is not in principle, but in computational power and interface technology, sensory input, output. This trajectory makes the simulation hypothesis feel less like fantasy and more like a predictable, if distant, technological milestone for any sufficiently advanced civilization. Brain-computer interfaces and full-dive VR. A roadmap. The key to an indistinguishable simulation is bypassing the senses and interfacing directly with the brain's sensory and motor cortices. Advances in Bowsley, neural lace technology, and Abisonomy, BCIs, like those pioneered by Neuralink, aim to do this for medical purposes. Combined with an understanding of how the brain constructs reality, this could lead to Bauer FOE, full dive VR, where a user's consciousness is fully immersed in a simulated environment, with the brain accepting it as completely real. This is the technological bridge from running a universe simulation out there on a computer to Wetsunix hosting conscious experiences within one. It shows a clear, if long, path to creating the kind of simulations Bostrom envisioned. The simulation singularity. When simulated realities outnumber base reality. This is a hypothetical future point where the total number of conscious beings living in simulated realities exceeds the number in the base, physical reality. At this simulation singularity, a random conscious being is more likely to be simulated than biological. This would represent the ultimate fulfillment of Bostrom's statistical argument. It would also create a bizarre cosmic ecology, layers upon layers of simulated realities, each with potentially different laws running on the computational substrate of the layer above, with the original base reality possibly lost to memory or myth. The philosophical implications for free will, identity, and meaning. Free will. If the universe is deterministic code or pseudorandom algorithm, is free will an illusion? Our choices might be the output of a complex calculation. Some argue compatibilism, that free will is about acting according to one's own internal reasoning, even if determined, could still hold within the simulation. Identity. If consciousness is an external stream, you are not your body. Your identity is that of the player, not the avatar. This dissolves the mind-body problem but creates a new duality. Meaning, if life is a simulation for someone else's research or entertainment, does it rob our lives of intrinsic meaning? Or does meaning derive from our subjective experience and relationships, regardless of the substrate? This forces a re-evaluation of existentialism. Is life less real if it is simulated? The philosophical debate. This hinges on the definition of real. If real means made of matter, energy in a base reality, then simulated life is not real. If real means causally consistent, having experiential qualia, and obeying immutable laws, then simulated life is just as real. The pain, love, and wonder felt by a simulated being are genuine experiences. The atoms may be data, but the information patterns and their causal consequences are real. This is the how realism. Position. A sufficiently detailed simulation isn't a fake reality. It's a different kind of real reality. Religious interpretations are programmers, gods, a modern creation myth. The simulation hypothesis inevitably resonates with theology. Programmers as creator gods, the beings who initiated the simulation possess godlike attributes. They created our universe, set its laws, constants, and are omnipotent within its framework, can alter code. They are possibly omniscient regarding our state, having access to all data. Miracles as interventions. Miracles or anomalous phenomena could be interpreted as direct code modifications or interventions by the programmers, Chitaka admin users. Afterlife as log-off. The death of the body, avatar, could mean the conscious player logs off and returns to the base reality. However, key differences remain. These gods are not necessarily supernatural. They exist in a higher physical reality, maybe multiple, a team, and may not be all loving or even aware of individual simulated beings. It provides a naturalistic technological framework for age-old questions of creation and transcendence. Updating ancient myths for a digital age. The simulation as a scientific, not theological framework. The core distinction is methodology and mechanism. Theology typically relies on revelation, faith, and supernatural causation. The simulation hypothesis, in its scientific form, proposes a naturalistic mechanism within a broader, but still physical reality. The programmers are not supernatural deities, but entities in a base reality who use technology, however advanced, that obeys the physical and computational laws of their universe. The hypothesis asks us to look for empirical evidence, glitches, lattice effects, and make testable predictions. It is an attempt to explain our reality using the language of information science and physics, not metaphysics. The potential purpose, scientific research, entertainment, ancestor simulation, art, or accident. If it's a deliberate simulation, the motivation is a major unknown. Scientific research. We could be part of a cosmological model, a sociology experiment, or a test of fundamental physics run by base reality scientists. Entertainment. An advanced civilization's version of an immersive video game or interactive drama. Ancestor, simulation. The Bostrom Classic, a historical recreation run by our descendants. Art, a form of generative or experiential art, a cosmic sculpture. Accident to a natural process. The simulation might not be run by anyone. It could be a self-organizing computational structure that emerged naturally in the base reality, akin to a complex crystal or a spontaneously formed virtual environment. This is the most disorienting possibility. We are in a process with no purpose, author, or audience. The simulation escape problem. Is it possible or even desirable? The sci-fi trope of escaping the simulation faces immense logical hurdles. Substrate dependence. Your consciousness, if it is a process running on the simulation's hardware, is made of the simulation's code, solid data. There is no you independent of it to extract. If you are an external player, you're already outside. The containment problem. Any escape plan, e.g., hacking the physics, would itself be a process within the simulation, likely anticipated and contained by the simulation's security protocols. Desirability. The base reality could be incomprehensible, hostile, or barren compared to our rich world. Escaping might mean annihilation of the self or existence in a form we cannot fathom. The goal may shift from escape to understanding. The information theoretic limits. Can we learn anything about the base reality? We are likely, and about to say about, informationally isolated. Any probe or experiment we conduct uses the Maltauer snare, rules and tools of our simulation. It's like a character in a video game trying to learn about the C++ compiler or the GPU it's running on, using only in-game physics. The base reality's laws could be utterly different. However, we might infer constraints. The base reality must support computation at least as complex as our universe. It must have concepts of mathematics and logic, or our simulated logic is a subset of theirs. Any detectable glitch is a tiny data leak that gives a fractional, encrypted glimpse of the underlying architecture, but likely not its nature. The simulators may have hidden or encrypted their presence. A robust, long-running simulation would likely have error correction and containment protocols. Obvious signatures of a lattice or artifacts would be smoothed over. The source code would be obfuscated. The simulator's primary goal, if research, might be non-interference. To avoid contaminating the experiment, their presence would be deliberately hidden, making the hypothesis difficult to falsify. This leads to a chopped simulation paranoia. Any null result in our glitch searches could mean we're not on a simulation, or that we're in a very well-designed one. The simulation may contain deliberate puzzles or Easter eggs. Conversely, the simulators might have left intentional clues, not as errors, but as Easter eggs, challenges, or signatures. This could range from elegant mathematical constants, like the fine structure constant appearing in unexpected places, to seemingly arbitrary but solvable cosmic anomalies. The search for such messages is analogous to the search for extraterrestrial intelligence, SETI, but looking for artifacts in physics rather than radio signals. It presupposes the simulators are communicative and want to be discovered, which is a significant assumption. The risk of simulation shutdown. Is it a cosmic existential threat? If the simulation is a deliberate project, it could be terminated. Reasons could include the research period ending, ethical concerns, resource relocation, boredom, or because we, the Sims, are about to discover something that threatens the simulation's integrity. like learning to hack it. This presents a new category of existential risk beyond astrophysical threats. There is no possible defense against it from within. This risk is only meaningful if the simulation is temporary and monitored, which we cannot know. Could we send a message to the simulators? Should we? Could we? Any message would be an action within the simulation. We might try to create a physics-defying event, so anomalous it triggers a review by the system's administrators, or arrange matter in a pattern that signifies intelligence to an outside observer, like drawing a prime number series across the solar system. Should we? This is a profound, interstellar-style dilemma. Contact could be positive, elevating our status, gaining knowledge, or catastrophic, triggering a shutdown or drawing malicious attention. Given our total ignorance of the simulator's motives, it is a gamble of cosmic proportions. Prudence might dictate not drawing attention, especially if the simulation appears stable and benign. The potential for nested simulations and infinite regress. This is a logical extension. If base reality civilization, it can simulate universe B, then a sufficiently advanced civilization within B could simulate universe C, and so on. This creates a simulation hierarchy. The infinite regress is problematic. It requires infinite computational resources or a turtles all the way down paradox. A more likely model is a finite stack. Each deeper simulation runs on a subset of the computational resources of the layer above, imposing practical limits on depth and fidelity. In a finite stack, the top base reality might be unknowable, but it also means there is an ultimate, non-simulated reality somewhere. Does the hypothesis lead to solipsism? Not necessarily. Solipsism is the idea that only one's own mind is sure to exist. The simulation hypothesis does not imply this. In fact, it offers a robust argument against it. Other simulated minds. Other people in the simulation are as real as you are. They are similarly instantiated consciousnesses, either as external players or as complex NPCs with qualia. Your subjective experience is not privileged. Shared reality. The simulation provides a consistent, objective environment that all conscious agents interact with. Their actions have causal consequences for you, and vice versa. The hypothesis suggests we are all in the same boat within the simulation. It is a collective solipsism of the simulated world, not an individual one. Your neighbors are as real as you are, sharing the same ontological status. The psychological impact of accepting the hypothesis. Embracing the possibility that reality is a constructed simulation can induce a profound makshabari ontological shock, disrupting core assumptions about existence. This can manifest in several ways. Existential dread or nihilism. The sense that life, struggle, and meaning are just a simulation can lead to feelings of pointlessness or cosmic insignificance, as if one's experiences are part of a game or experiment they didn't consent to. Liberation or cosmic perspective. Conversely, it can foster a sense of profound wonder and curiosity, reducing the weight of earthly concerns. If the base reality is malleable code, it can inspire a more playful, creative, or exploratory approach to life. Simulation, paranoia. A hypervigilance for glitches, or a persistent feeling of being observed by unseen administrators. This can border on delusional thinking if not tempered by scientific rigor. Shift in values. It may elevate the importance of information, consciousness, and relationships, over purely material pursuits, as these become the fundamental substance of a simulated reality. How the scientific community is slowly engaging conferences, papers, and serious discussion. Once considered fringe, the hypothesis is now a subject of legitimate, if niche, academic discourse. This is evidenced by dedicated conferences, events like Are We Living in a Simulation? At the American Museum of Natural History, 2016, and panels at major physics conferences where respected theorists like James Gates, David Chalmers engage in debate, peer-reviewed literature, papers exploring testable signatures, geek, lattice effects and cosmic rays, or the informational foundations of physics are published in reputable journals. The discussion has moved from pop science magazines to venues like Foundations of Physics. Pedagogical use. It is employed in university courses on philosophy of science, cosmology, and quantum foundations as a powerful tool to interrogate concepts of reality, evidence, and the limits of scientific inquiry. Prominent supporters and detractors in physics, the hypothesis has a divided reception. Open, supportive, or intrigued. Neil deGrasse Tyson has stated he finds the odds very high that we are in a simulation. Michio Kaku treats it as a serious technological possibility stemming from future computing power. James Gates. His discovery of error-correcting codes, like those in browsers, embedded in supersymmetry equations, led him to publicly ponder the analogy. David Deutsch. His work on quantum computation and the fabric of reality is highly consonant with a computational universe. Skeptical, critical. Sabine Hossenfelder, a leading critic arguing it's an untestable, distracting metaphor that generates no new physics and is a science stopper. Lisa Randall has dismissed it as fun speculation but lacking any empirical foundation. Most practicing physicists maintain a default, healthy skepticism. They demand testable predictions and view it as philosophy, until it produces concrete, falsifiable hypotheses that can drive experimental programs. The hypothesis as a productive thought experiment. Its greatest contemporary value is not as a proven theory, but as a Mauricito, powerful philosophical and scientific probe. It forces a rigorous examination of foundational questions. What do we mean by real? What constitutes ultimate evidence for the laws of nature? What are the limits of scientific knowledge from within a system? Is there a fundamental difference between a simulated consciousness and a biological one, if both have identical experiences? By stressing our basic assumptions, it can catalyze novel approaches to long-standing problems in quantum mechanics and cosmology. Its influence on foundational physics research directions. While not a formal research program, its themes are deeply embedded in several cutting-edge fields. Quantum gravity, theories like loop quantum gravity, and causal dynamical triangulations directly propose a discrete granular spacetime, a core tenet of the digital physics underpinning the simulation idea. Quantum information science. The field that asks, is the universe a quantum computer? Research into quantum entanglement, teleportation, and computation treats physics as information processing. Cosmology. High-precision analyses of the cosmic microwave background, CMB, for statistical anomalies like non-Gaussianities or preferred directions, are, in effect, tests for signatures of a finite constructed or coded initial state. the convergence of computer science, information theory, and physics. This is a defining trend of 21st century fundamental science. The simulation hypothesis is both a product and a driver of this convergence. Concepts like algorithmic complexity, data compression, and error correction are no longer just computer science topics. They are essential tools for understanding black hole entropy, holography, quantum randomness, and the possible emergence of spacetime from informational relationships. The ultimate test may come from a theory of everything, TOE, a final, unified theory that successfully merges quantum mechanics and general relativity could, by its TOE, form, and character, provide the strongest indirect evidence for or against a computational reality. The TOE wouldn't say we are in a simulation, but its nature would be deeply suggestive. If the final TOE is computational and elegant, like a beautiful piece of code, if the TOE is not a set of continuous differential equations, but rather a simple, finite, and breathtakingly elegant set of discrete rules, or an algorithm, a short program that generates the complexity of the universe, it would be powerfully indicative of an informational or design substrate. This would be the discovery of the universe's potential source code. If the TOE is messy and arbitrary, it might still suggest an ad hoc construction. Paradoxically, a TOE that is a convoluted and elegant patchwork, filled with dozens of inexplicably fine-tuned constants and ad hoc rules, could also point toward a simulation. It might resemble spaghetti code, a functional but messy construction built for a specific purpose, to produce our particular universe, rather than arising from simple, beautiful, fundamental principles. It would look engineered, not elemental. We may never have definitive proof, only increasing degrees of plausibility. This is the most likely epistemological outcome. Absolute, incontrovertible proof from within the simulation may be impossible by its very nature, like a character proving the computer it runs on. Instead, we may approach a conclusion through a preponderance of evidence, an accumulation of vague, stubborn anomalies, with no better explanation, a thing adaptados that is inexplicably computational. The future pabaxim, technological achievement of creating our own high-fidelity, conscious simulations, which would make the statistical argument, Bostrom's trilemma, feel overwhelmingly persuasive. The hypothesis may never transition from likely to proven, but it could become the most coherent and useful paradigm for understanding a universe that behaves in every testable way, like an immense self-consistent computation. The quest itself, forcing us to the absolute limits of science, philosophy, and reason, is perhaps its most valuable contribution. Recapping the strongest evidence: Planck scale, holography, mathematical underpinnings, potential anomalies. The most compelling arguments for taking the hypothesis seriously are not glitches, but fundamental features of established or cutting-edge physics. Planck scale. The existence of fundamental, indivisible units of length and time suggests a discrete, pixelated reality, a hallmark of digital systems. Holographic principle. The revelation that the information content of a region scales with its surface area, not volume, is a precise form of cosmic data compression, indicating reality may be a projection. Unreasonable effectiveness of mathematics. The universe's obedience to elegant, discoverable mathematical laws suggests it is built on a logical, rule-based structure, a code base. Potential anomalies. While not proof, persistent puzzles like the immune GTN2 discrepancy, the lithium 7 problem, and large-scale CMB alignments, axis of evil, are the kind of unexplained bugs one might find in a complex simulation. Recapping the major counterarguments: untestable, metaphysical, an analogy, not a theory. The primary scientific criticisms are substantial. Lack of falsifiability. In its broadest form, it's unfalsifiable. Any observation can be dismissed as part of the simulation. To be science, it must make unique, risky predictions, like the cosmic ray lattice test. It's metaphysics, not physics. Critics argue it doesn't solve a single equation or predict a new particle. It's a philosophical interpretation of physics, not a physical theory itself. The analogy trap. It may be a compelling taku metaphor. The universe computes, mistaken for a literal description. A useful analogy is not proof of an identical mechanism. The simulation hypothesis as a modern mythology that uses the language of our time, computation. Every age interprets the cosmos through its dominant technology. The 17th and 18th centuries saw a Pyrrhus clockwork universe. The 19th century offered an organic evolving universe. The late 20th century gave us the universe as a quantum system. The 21st century paradigm, born in the information age, is the universe as a computational process. It's a creation myth for the digital era, replacing the watchmaker with the programmer and divine law with source code. It resonates because it uses the language we understand best. Comparing it to past paradigms, the clockwork universe, the organic universe, clockwork universe, Newton-Laplace. The cosmos as a perfect deterministic machine set in motion by a divine engineer. It emphasized order, predictability, and external design. Organic evolutionary universe, Darwin-Spencer. The cosmos as a growing, evolving, self-organizing entity. It emphasized change, emergence, and internal process. Computational, simulated universe. Synthesizes both. It has the co-gigabit designed rules of the clockwork and the fambytoider, emergent complexity of the organic view. The design is in the initial algorithm. The richness unfolds from its execution. Is the simulation hypothesis the 21st century's dominant metaphysical framework? It is becoming a leading candidate. It is not yet dominant in academic philosophy, but it is arguably the most influential new metaphysical idea in popular and tech culture. It provides a narrative that is naturalistic, avoiding the supernatural, technologically awe-inspiring, capable of addressing existential questions of origin, purpose, and fine-tuning. It competes with, and often absorbs, narratives from traditional religion, pure materialism, and multiverse theories. Its impact on culture, film, literature, and art for the next century. Just as the clockwork universe shaped Enlightenment art and the existential universe shaped 20th century modernism, the simulation framework will deeply influence 21st century narrative and aesthetics. Narrative tropes. Stories will explore identity in layered realities, the ethics of creation, the search for the developer, and the nature of glitches. Visual aesthetics. Art and film will visually represent the code layer beneath reality. Geometric lattices, flowing data, glitch art, and the merger of organic and digital forms. Philosophical theme. The dominant question shifts from who made us to what is our system running on and why? The danger of nihilism first serves the opportunity for profound curiosity. The hypothesis presents a fork in the road for the human psyche. The nihilistic path. Nothing is real, so nothing matters. This leads to apathy, existential dread, and a devaluation of lived experience. The curious path. Everything is real in a new way. It's made of information and purpose. Let's understand it. This fosters a spirit of radical exploration, wonder, and a drive to uncover the deepest mechanics of existence. The choice is between seeing the simulation as a prison or as the most fascinating puzzle imaginable. If we are in a simulation, the project of science is literally reverse engineering the source code of reality. This reframes the entire scientific endeavor with thrilling clarity. Physicists are not just law discoverers, they are debuggers and decompilers. Every experiment is a probe for the runtime environment. The standard model is a compiled library. Finding a toe would be obtaining the commented source code. This is a powerful, motivating narrative for fundamental research. This is the ultimate goal of physics, simulation or not. Remarkably, the goal remains identical. Whether the universe is a simulation or base reality, the aim of fundamental physics is to discover the somewhat most fundamental, concise set of rules that govern everything. The simulation hypothesis simply suggests what the nature of those rules might be. Computational. The quest for a understanding is unchanged. Only the anticipated character of the answer is different. The potential for cheat codes. If we understand the code deeply, can we manipulate it? This is the ultimate speculative frontier. If we ever achieve a complete toe that is truly computational, the next question is, can we write to the universe as well as read it? Could we, with unimaginable energy and precision, input new commands? Cheat codes could mean manipulating physical constants locally, bypassing conservation laws, or editing space-time geometry. This would be the pinnacle of technology, not engineering within the laws, but engineering of the laws. It represents the transition from being users of reality to becoming, in a limited sense, co-programmers. This is the farthest horizon of the hypothesis, blending into pure science fiction, but it logically follows from its core premise. It marks the point where humanity would truly graduate from being mere characters in the simulation to becoming aware of and potentially interacting with the console. The moral responsibility that would come with such power. If humanity ever advanced to the point of understanding and potentially manipulating the foundational code of reality, it would inherit a moral burden of cosmic proportions. This power, akin to playing God, would require an ethical framework far beyond anything currently imagined. Decisions would involve non-maleficence, ensuring any rewrites do not cause unintended suffering or erase conscious beings. Justice. Who controls this power? Could it create infinite inequality between those who can manipulate physics and those who cannot? Stewardship. The responsibility not to crash or corrupt the entire simulation, our universe, through careless experimentation. Such power would demand a maturity and wisdom we have not yet demonstrated as a species. The simulator's ethics. Are they responsible for suffering and the simulation? This is a profound ethical dilemma for the hypothetical creators. If they are conscious, moral agents who deliberately initiated a simulation containing beings that can suffer, they bear a paradios, creator's responsibility. This makes natural evils, disease, natural disasters, and the potential for moral evil, war, cruelty, seem either monstrously negligent or part of a callous experiment. Possible justifications within their ethics could be: the suffering is necessary for the simulation's purpose, e.g., to study resilience, complexity, or ethics itself. The suffering isn't real to them. They might view simulated pain as no more ethically significant than a character's pain in a movie. They have a prime directive, a strict non-interference policy, even to alleviate suffering to preserve the integrity of the simulation. Their ethics, or lack thereof, would be the defining characteristic of our creators. Is our perceived free will an illusion granted by complex algorithms? In a deterministic or pseudo-random simulation, every thought and decision could be the output of an immensely complex algorithm processing initial conditions and inputs. Our sense of free will, the feeling of deliberation and choice, would be a sophisticated embedded feature of the simulation designed to make agents, US, behave in realistic, complex ways. This is known as compatibilism. Free will as the experience of making choices determined by our own internal programming, desires, memories, reasoning. We would have user-level free will, but not administrator-level freedom to act outside the code. The nature of time. Is it fundamental, or just the sequential processing of states? In most physical simulations, time is not a fundamental dimension, but an emergent property of sequential state updates. The simulation has a clock cycle, like Planck time. Applying this to our universe suggests that time may not flow independently. It may be the ordered processing of information from one state to the next. The arrow of time, entropy increasing, could be a feature of this processing order, a built-in increase in data's complexity, or a one-way logging function. Could the simulation be paused, rewound, or saved? From an external perspective, almost certainly. Paused. The simulator could halt its processor, freezing every conscious experience at a moment. Rewound, restored. By reverting to a saved state, a backup file, the entire universe could be reset to a prior point. Our continuity of memory would be erased or overwritten. Saved. Multiple branches or saved games could exist, meaning countless versions of you might exist in parallel save files. This resonates with the many worlds interpretation of quantum mechanics, which could be implemented via branching save state system. The block universe. Theory of time from relativity versus the flowing time of perception. Physics presents a stark dichotomy. Block universe, eternalism. From relativity, all of time, past, present, future, exists simultaneously in a static, four-dimensional block. There is no special now. The flow of time is an illusion. Flowing time, presentism. Our conscious perception is of a moving now with an uncertain future and a fixed past. This is psychologically fundamental, but difficult to square with physics. These views are fundamentally opposed in standard physics, but a simulation framework can reconcile them. In a simulation, both could be true. The simulation hypothesis elegantly resolved the conflict. The block universe is the saved file. The entire timeline exists as a complete data structure on the simulator's storage system. This is the objective, external view. The flowing time is the runtime. Our conscious experience is the karike, sequential reading and execution of that data structure. The cursor of our perception moves through the block, creating the illusion of a flowing present. The block is the whole movie. The flow is the projector. playing it frame by frame to a conscious observer. Death in the simulation. Is it a character deletion, a transfer of consciousness, or just a process halt? The meaning of death depends entirely on the architecture of consciousness. Character deletion, a NPC termination. If consciousness is a purely simulated process within the avatar, death is the permanent deletion of that specific data structure. The self ends. Transfer of consciousness, chuck a player log off. If consciousness is an external player interfacing with an avatar, death is the disconnection from that avatar. The player's consciousness persists elsewhere, in the base reality or a different simulation. Process, halt. The conscious process is paused or halted in a simulation that can be restored from a backup. This death is not permanent. The process could be restarted from a save point, though without continuity. The potential for afterlife scenarios within the simulation's rules. The simulation's code allows it. Afterlife need not be supernatural. Backup and restore. Consciousness is periodically backed up. Upon bodily death, it's restored to a new body or a different environment. Heaven, hell servers, respawning. A default function for conscious agents, transferring them to a new instance or simulation after death. Afterlife as a different process. Death triggers the execution of a separate pre-written subroutine, a post-mortem simulation, tailored to the individual's beliefs or actions, a karmic algorithm. These are not spiritual realms, but engineered features within the simulation's architecture. The ultimate question: why is there something rather than nothing? The simulation hypothesis does not answer this question. It kicks it upstairs. It explains why a particular something, this universe, exists, because it was instantiated in a computer in a base reality. But it then forces the same question upon the base reality. Why is there something, the base reality, its laws, its simulators, rather than nothing? It transforms the question from a metaphysical one about our cosmos to its physical or metaphysical one about the outermost reality. It suggests that if existence has an ultimate reason, it lies in the logic or necessity of that final, non-simulated layer, a layer whose nature we may be forever incapable of accessing or comprehending. The hypothesis offers a potential mechanism for our existence, but not an ultimate explanation for existence itself. The simulation hypothesis offers an answer, because someone or something in a base reality ran a program. For the persistent existential question, why is there this universe? The hypothesis provides a clear, mechanistic answer. Our universe exists as a contingent artifact of action in a more fundamental reality. It is not a necessary, eternal entity. It is a created one. Its existence is akin to that of a novel or a video game. It exists because an author or programmer outside the system initiated it. This replaces metaphysical mystery with a, potentially, physical causation. But it just pushes the question back. Why is there a base reality? This is the fundamental limitation and philosophical recursion of the hypothesis. It solves the mystery of our existence by positing a deeper reality, but it utterly fails to explain that deeper reality. The ultimate why is there something rather than nothing question remains unanswered. The hypothesis simply relocates the mystery to an inaccessible domain, offering no insight into whether the base reality is necessary, eternal, self-caused, or itself simulated. It's an explanatory placeholder, not a terminus. The possibility of an infinite regression of simulations, or a single, primordial reality. This presents two stark metaphysical possibilities: infinite regress, a never-ending chain of simulations within simulations, a turtles all the way down scenario. This is logically and computationally problematic, as it requires infinite computational resources or leads to circular causality. A single, primordial base, reality. There is a top-level, non-simulated reality. The original, real universe where the first simulation was run. This reality's existence must be accepted as a brute fact. This is the more coherent, if still unexplained, endpoint. The quest for understanding would then seek the laws of that ultimate reality. The existential vertigo of the hypothesis. Engaging deeply with the idea can induce a profound cognitive and emotional disorientation. Existential vertigo. It involves loss of ontological certainty. The solid ground of reality dissolves into a contingent informational process. Scale shock. Confronting the possibility that our entire cosmos, with all its history and grandeur, is a Bao subroutine on an alien computer. Purpose anxiety. The potential reduction of all human striving, art, love, and war to data points in an experiment or elements of entertainment. This vertigo is the psychological price of taking the idea seriously. Concluding the physicists' slip up. It was admitting this is no longer just science fiction. The titular slip up is not a confession of proof, but a breach of scientific caution. It is a respected physicist conceding, in a moment of intellectual honesty, that the hypothesis has crossed a threshold. It is no longer dismissible as mere fantasy, but must be treated as a free, legitimate framework for inquiry, a speculative but coherent model that intersects with serious work in quantum gravity, information theory, and cosmology. The slip was treating a sci-fi trope with the seriousness of a scientific hypothesis. The final point, the simulation hypothesis, forces us to take nothing about reality for granted. This is its most enduring and valuable function. It is our instrument of radical doubt. It compels us to question assumptions we treat as axioms, the continuity of space and time, the fundamentality of matter, the nature of consciousness, and the very objectivity of the laws we discover. It is a philosophical acid test for our most deeply held beliefs about existence. It is a catalyst for the most fundamental questions in science and philosophy. The hypothesis doesn't provide answers so much as it supercharges the questions. It injects new urgency and perspective into ancient and modern puzzles. Science. What is the ultimate nature of physical law? Is information more fundamental than matter? Philosophy. What is consciousness? What is real? Do we have free will? Theology. What is creation? What is the nature of a creator? It acts as a synthesizer, forcing these disparate lines of inquiry to confront one another. Whether true or not, considering. It expands our understanding of what is possible, even as a probable falsehood. The hypothesis has immense value. It stretches the imagination and expands the conceptual landscape of science. By considering a universe that is computational and contingent, we develop new tools, ask new questions of our data, and conceive of new types of explanations. It is a Yin stress test for our current paradigms, revealing their strengths and hidden assumptions. The ongoing search continues in quantum labs, cosmological surveys, and particle colliders. The quest for answers is not philosophical navel-gazing. It is an empirical, technical grind. The search for evidence, or for a better theory, plays out in quantum labs, testing the limits of randomness, entanglement, and quantum computing. Cosmological surveys, mapping the CMB and large-scale structure for anomalies, hinting at finite or constructed geometry. Particle colliders, probing ever higher energies for deviations from the standard model that could point to deeper, perhaps computational structures. This is where the hypothesis meets the hard, unyielding surface of observable reality. We are all, willingly or not, participants in the greatest detective story imaginable, determining the fundamental nature of our own existence. This is the human condition framed by the hypothesis. We are not passive inhabitants of a given world. We are active investigators trapped inside the mystery. Every scientific experiment, every philosophical argument, every moment of introspective wonder is a clue we are gathering. The case is the cosmos itself, and the answer we seek, whether it's a theory of everything, proof of simulation, or something beyond our conception, would be the ultimate revelation. Our shared involuntary participation in this search binds humanity together in a project of supreme significance. The self-universe, trying to understand itself. The simulation hypothesis offers an answer, because someone or something in a base reality ran a program. For the persistent existential question, why is there this universe? The hypothesis provides a clear, mechanistic answer. Our universe exists as a contingent artifact of action in a more fundamental reality. It is not a necessary, eternal entity. It is a created one. Its existence is akin to that of a novel or a video game. It exists because an author or programmer outside the system initiated it. This replaces metaphysical mystery with a potentially physical causation. But it just pushes the question back. Why is there a base reality? This is the fundamental limitation and philosophical recursion of the hypothesis. It solves the mystery of our existence by positing a deeper reality, but it utterly fails to explain that deeper reality. The ultimate why is there something rather than nothing question remains unanswered. The hypothesis simply relocates the mystery to an inaccessible domain, offering no insight into whether the base reality is necessary, eternal, self-caused, or itself simulated. It's an explanatory placeholder, not a terminus. The possibility of an infinite regression of simulations, or a single, primordial reality. This presents two stark metaphysical possibilities: infinite regress, a never-ending chain of simulations within simulations, a turtles all the way down scenario. This is logically and computationally problematic, as it requires infinite computational resources or leads to circular causality. A single, primordial base, reality. There is a top-level, non-simulated reality. The original, real universe where the first simulation was run. This reality's existence must be accepted as a brute fact. This is the more coherent, if still unexplained, endpoint. The quest for understanding would then seek the laws of that ultimate reality. The existential vertigo of the hypothesis. Engaging deeply with the idea can induce a profound cognitive and emotional disorientation. Existential vertigo. It involves loss of ontological certainty. The solid ground of reality dissolves into a contingent informational process. scale shock, confronting the possibility that our entire cosmos, with all its history and grandeur, is a Fambetabao subroutine on an alien computer. Purpose anxiety, the potential reduction of all human striving, art, love, and war to data points in an experiment or elements of entertainment. This vertigo is the psychological price of taking the idea seriously. Concluding the physicists slip up. It was admitting this is no longer just science fiction. The titular slip up is not a confession of proof, but a breach of scientific caution. It is a respected physicist conceding, in a moment of intellectual honesty, that the hypothesis has crossed a threshold. It is no longer dismissible as mere fantasy, but must be treated as a pretty legitimate framework for inquiry, a speculative but coherent model that intersects with serious work in quantum gravity, information theory, and cosmology. The slip was treating a sci-fi trope with the seriousness of a scientific hypothesis. The final point, the simulation hypothesis, forces us to take nothing about reality for granted. This is its most enduring and valuable function. It isn't our instrument of radical doubt. It compels us to question assumptions we treat as axioms, the continuity of space and time, the fundamentality of matter, the nature of consciousness, and the very objectivity of the laws we discover. It is a philosophical acid test for our most deeply held beliefs about existence. It is a catalyst for the most fundamental questions in science and philosophy. The hypothesis doesn't provide answers so much as it supercharges the questions. It injects new urgency and perspective into ancient and modern puzzles. Science. What is the ultimate nature of physical law? Is information more fundamental than matter? Philosophy. What is consciousness? What is real? Do we have free will? Theology. What is creation? What is the nature of a creator? It acts as a synthesizer, forcing these disparate lines of inquiry to confront one another. Whether true or not, considering. It expands our understanding of what is possible, even as a people probable falsehood. The hypothesis has immense value. It stretches the imagination and expands the conceptual landscape of science. By considering a universe that is computational and contingent, we develop new tools, ask new questions of our data, and conceive of new types of explanations. It is a keen stress test for our current paradigms, revealing their strengths and hidden assumptions. The ongoing search continues in quantum labs, cosmological surveys, and particle colliders. The quest for answers is not philosophical navel-gazing, it is an empirical, technical grind. The search for evidence, or for a better theory, plays out in quantum labs, testing the limits of randomness, entanglement, and quantum computing. Cosmological surveys, mapping the CMB and large-scale structure for anomalies, hinting at finite or constructed geometry. Particle colliders, probing ever higher energies for deviations from the standard model that could point to deeper, perhaps computational structures. This is where the hypothesis meets the hard, unyielding surface of observable reality. We are all, willingly or not, participants in the greatest detective story imaginable, determining the fundamental nature of our own existence. This is the human condition framed by the hypothesis. We are not passive inhabitants of a given world. We are active investigators trapped inside the mystery. Every scientific experiment, every philosophical argument, every moment of introspective wonder is a clue we are gathering. The case is the cosmos itself, And the answer we seek, whether it's a theory of everything, proof of simulation, or something beyond our conception, would be the ultimate revelation. Our shared involuntary participation in this search binds humanity together in a project of supreme significance. The self universe, trying to understand itself,